vector is minus 2, 1, 2.
Minus 2, 1, 2. Okay, thanks.
Any answers? Anyone found U2?
Is it 0 1 0 only?
5 to 4. Yeah, Pranav, your answer is right. So let's not delay, let's do it. So, where did it go? Okay. So, we find U2 and using Gram-Schmidt, we get U2 to be 5 by 9, 2 by 9, 4 by 9. Now we need to make this to the length should be 1, right? So the norm, its norm is under root 5 by 3. So I get my U2 hat to be 5 by 3 root 5, 2 by 3 root 5, and 4 by 3 root 5. So this is my U2. Okay. Did you get this answer? 5 by 9, 2 by 9, 4 by 9?
No, ma'am.
No. So this is a Gram-Schmidt process, right? This is what we do. This is the process. So uh, you do so one.
Ma'am, in the last we multiplied with U1.
Yeah, we multiplied with U1.
And can you please do it for only U2?
Yeah, so U2, it is Y2 minus inner product of U1 with Y2 with U1 into U1 divided by its norm. So U1 norm is already 1, so that is okay. And Y2 I had taken to be 101, right? So 101, and what is the inner product of U1 with Y2? U1 is minus 2 by 3, 1 by 3, 2 by 3. And Y2 is 101. So the dot product will come out to be minus 2 by 3.
Minus 2 by 3.
So I can just write plus 2 by 3 here, right? And then 1 by 3 again comes here, so it's 2 by 9. Minus 2, 1, 2. Right? And
Again,
then you
1
get
by 3 from where, ma'am, it comes?
from here, y1.
Okay, okay.
Yeah? So you get minus 4 by 9, 2 by 9, 4 by 9. And then add with 100, you get 5 by 9, 2 by 9, 4 by 9.
Okay, ma'am.
Now its length is root 5 by 3. So you get U2 hat to be this. Now this is a U2. Sorry, U2. After this, you need to find your third vector, that is U3. So again, you proceed with the same, and you get U3
And
to be
5 by 3 root 5, ma'am, is that?
root 5 by 3.
U2, root 5 by 3, root 2, 5 by 2.
Root 5 by 3.
Okay. Okay,
Ma'am,
ma'am.
how you found U1? Sorry,
U1, I
Y1?
had just taken it to be Y1, no?
Okay, okay.
Yeah. This is what you do. You take,
Uh-huh.
keep one vector as the same.
Okay,
No,
ma'am.
actually, I'm asking about this U2 hat. How do you get that, ma'am,
This
from...
is 5 divided by 9. So 5 divided by 9 divided by root 5 by 3.
Oh, root
This
5
is
by
5
3 is
by
its
3
norm.
root 5.
Okay, 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 ma'am.
Okay.
U1's norm will always be 1, right?
Uh, yeah, like in this case, it turned out to be norm length 1, but if it was not, we'll have to make it 1.
Uh, but when we did U1 is equal to Y1 divided by its norm, didn't it become norm 1?
Yeah, this is norm 1, but I'm saying, like, let's say this y1 we had taken. So our y1 comes out to be minus 2 by 3, 1 by 3, 2 by 3. But
Hmm.
let's say if this was not the case,
Hmm.
right? If this norm was not, if this length was not 1, then we had to divide it by its norm, no? For u1.
Yeah, but in by finding U2, we're saying here it is Y2 minus inner product of U1 Y2 multiplied by U1 divided by U1's norm squared, right?
Hmm.
So, but since we made the norm of Y1, which is U1 ultimately, to be 1,
It is
so
1.
U1 will always be 1, no? Or am I
Yeah,
wrong?
like if you make it like length 1, then it will be 1.
But the first step makes it 1 anyhow.
No, let's say I'm not normalizing it here. Okay, let's say I did not normalize. I just have whatever y1 I had. I kept it like that. Then
Okay,
using that y1, I used find my y2 u2, and whatever u2 I got, using that I find my that u1 u2 I find my u3,
okay,
and then at the end I normalize. That is also okay.
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 Ma'am, but for norm, ma'am, norm for U2, we will get, we got root 33 by 9. So how do you get then root 5 by 3, ma'am? Actually, 5 square plus 2 square plus 4 square.
25 plus 4 plus 16, that is 45 by 81. 45 by 81 is 5 by 9.
Okay, ma'am.
So under root of 5 by 9 is under root of 5 by 3.
Okay, okay, ma'am.
Yeah. So using the Gram-Schmidt process, we find our U3 also, and we get this to be 0, 2 by root 5 and minus 1 by root 5. Okay. You can check the calculation. So what did we get at the end? We got, so we found our y1. This is y1. This is our y2, and this is our y3. Right. So now if we want to write A in terms of Q1 sigma Q2 transpose, I can write this as, so this is our Q1, right? This is your diagonal matrix. This is sigma, and this is Q2 transpose.
Can you go up, ma'am?
Hmm.
Okay. So, ma'am, how you got 3 root 5?
There, 3 root 5. Is it 3 root 5? No, I had explained it.
Okay. Okay. Divided by 3. Okay, ma'am.
So we found the SVD for the matrix A. That is this.
Ma'am, one question over here. So if we see the final matrix, so I can see only the first column is impacting because all the values we are getting in the first column are the final values ultimately. So second column and third column, I think in that case can be anything.
It can be anything. Yeah,
Very
depending
good.
on, yeah, it can be anything.
So if I say 1 by root 2 1 0 1, so that is again in normalized or vector. So it can be y2 and y3 as well.
Yeah, but you also need to check that all these like they should be or orthogonal, no?
Orthogonal. Okay.
Yeah, it's that is why we use this Gram-Schmidt process to get these y2 and y3, because in the initial case it was not orthogonal.
Right. So I'm giving you one vector. So let's say 1 by root 2, and the elements of vector are 1 0 1. So that is again orthonormal
Sorry,
to
can you repeat?
first one vector.
One
1 by root 2
one by root two.
and 1 0 1. I mean, this
Uh,
is the
this
outer part, 1 0 1 inside that.
okay.
I think 1 0 1. Right. So this
Hmm.
is again orthogonal to first vector.
Is it orthogonal to first? So first vector was minus 2 by 3, 1 by 3, 2 by 3. And your second vector is 1 by root 2, 0, 1 by root 2.
Yep.
Is it orthogonal? Minus 2 by 3 root 2 plus 2 by 3 root 2. Yeah, they are orthogonal.
And it is
Now you need to
orthonormal
check.
as well.
But now this has to be orthogonal to the third one also.
Yep. So I have one more, 1 by root 5,
Hmm.
0, 2, minus 1.
1 by root 5. Tell me again. 1 by root 5.
0, 2, minus 1. Same as 1. I mean, inside
Okay.
the
0
bracket.
to minus 1. 0 to minus 1 by root 5. Okay.
Right.
You check if these two are orthogonal. They are not, right?
Okay.
Yeah. All the pairs should be orthogonal, no?
Mhm.
Yeah. So that is why this E1, E2, like our standard vectors, they generally work. So
Okay. Okay.
don't have
Got
to
it.
think much, yeah.
I'm sorry, but what was the question again? What were we supposed to find?
The question was, no, you had to find the SVD, and we did found the SVD for this matrix. So what he asked is like this y2 and y3 can be anything, right? Because this is what we had chosen ourselves, right? This is one. This was our choice to choose y2 to
Yes.
be 1 0 0 and be 0 1 0. But let's say someone come with the vectors which are linearly independent and they are orthogonal also, then
Hmm.
it will then this process can give a different y2 and y3. That is what you were saying.
Okay.
So that is why we were coming with, like, he gave me two three options for the vectors, and we were checking that they are not all orthogonal to each other. So
So we have just decomposed Heaven's SVD for A.
yes, we did.
And what have we really achieved? We have just achieved it as in terms of the product of.
We found what is our Q1, we found what is our diagonal matrix, and we found what is our Q2 transpose.
What is special about Q1 and Q2?
So Q1 and Q1 should be orthogonal, Q2 should also be orthogonal.
Sorry, Q1 should be?
Q1 should be orthogonal, Q2 should also be orthogonal, right?
Okay. But since this Q2 is just a single value matrix,
In this case, it is like that, but it may not be always true. I mean,
so they
Q1
should be orthogonal matrices, and the center matrix should be a diagonal matrix,
diagonal matrix.
and the value in its diagonal.
We just had one sigma value, right? So we
Yeah.
just put three, and remaining would be zero.
Okay,
So
so the
yesterday,
diagonal matrix only contains the sigma values.
yeah. So yesterday we had seen a simple example, 2 cross 2 matrix, and
Yes.
from there we had decomposed the matrix A into its SVD form. So today, yesterday was a square case when the matrix was a square matrix, and today we saw like what happens when your matrix is a rectangular matrix.
So what is the purpose achieved through this SVD when you've got this Q1, Q2, and this?
Yeah, so I told yesterday, right? You have some tutorials in week 6. They are very good tutorials. So there you see the applications of these SVD.
Okay.
So there are 2 3 applications that is discussed in the tutorial. So that is what I
Right.
told. If you are interested, just watch it.
Okay.
So
So
it is generally used to reduce the size that any picture or any
image, that
graphs
is,
would
yeah,
be
one
stored in the
application for
system.
it.
Ma'am, this SVD form is used in that ridge regression, right?
SVD form is used in ridge regression.
Yes, ma'am. There was a similar formula in ridge regression where we use W minus W hat ML and transpose into covariance matrix and W minus W hat again. So that resembled SVD form, ma'am. So yeah.
Okay, yeah, I will check it. Yeah. All right. So one more way to write your A to B. So we had written A to B this Q1 sigma Q2 transpose, right? So let's say in place of Q1, I just the notation change I am doing here. So U sigma V transpose. Okay, it's the same thing. What Q1 is, what Q2 is. I'm just writing it as U and V. Now, what we are saying is this can also be written as some sigma times sigma I ui vi transpose. So this is also okay. Yeah. So this is also how you can write this A to B. Now,
Ma'am,
yeah,
if you don't mind, can you write the dimensions also?
dimensions of.
Q1 sigma Q2.
So sigma i's are they are singular values,
No,
right?
no, I mean the dimension. If A is m cross n, m cross n, then what will be the dimension of Q?
Ma'am,
I mean that.
yes, ma'am. I also have a similar doubt.
Yeah.
In the beginning of this question, you have written the dimensions of each and every this Q1, sigma, and Q2. How have you written them? Just like you
Yeah.
started the question when, yeah,
Uh,
that Q1 would be 3 cross 3 and all that.
oh, uh, so you have A, yeah, A to B Q1 sigma Q2 transpose. A
Yes,
was in this case A is what? This is some 3 cross
3 cross 1.
Like one.
matrix. Okay. So this A will be similar to so this Q, this sigma diagonal matrix. So you just put 3 cross 1. Okay. So if this is 3 cross 1, your Q1 should be what? 3
3
cross
cross
3,
3,
and this Q2 should be
1
1
cross
cross
1.
1. Yeah. Now what we are saying is this can also be written in this form. All right.
Ma'am,
So
how this form is being generated?
it just from so Q1, right? So this UIs are coming from Q1 and this VIs are coming from Q2.
Mm-hmm.
Okay. So sigma i's are the singular values that you have.
Okay.
So if you write it, so your UI, right? So if I, it will be sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose and so on. And each of this UI, so my let's say U1, so this is your matrix. This is on like M cross 1 matrix.
Mm-hmm.
Okay. This sigma I can, this is a just scalar. I can just
Scalar.
keep it.
Yeah.
And V1 transpose is V1 transpose like this.
Okay. Okay. Got it. So this
So,
sigma is different. This sigma is not that sigma. This
uh,
sigma is just an addition.
oh, this is addition. Yeah, right. This is
Yeah.
addition.
Yeah. That was the confusion. Okay.
Yeah, yeah. This
Ma'am,
is
can you
addition.
go up just for a second to the answer only? Slightly more. Okay. Okay, ma'am. Thank you.
Yeah, I think yesterday what I had written here, there was a mistake. So
Yeah.
Now, what is the upper limit of sigma in the different notation in the last year? I equals 1 to
this is summation. I varies from 1 to k.
k. And what is k here?
K can be like till what rank you want to go.
So in the study, okay.
Yeah. So you have rank 1. So rank 1 is rank 1 matrix will be just. So if I want rank 1, it will be just sigma 1 u1 v1 transpose.
So for a given question, how would we know or up to which rank we need to calculate? Say I want to, find A using this notation, then
Hmm.
how will I know what rank to take?
Uh, I think okay in the tutorial that you have seen, right? So there it has been done using some image, and the more you keep increasing the rank, and your image gets more clearer and clearer. So you'll have to keep changing, keep varying the ranks, and then you see which one gives you the better uh,
Yeah, higher
image.
the rank, the better the resolution of the image,
Yeah,
right?
better
So
the rank. Yeah, more the rank, better the result. Yeah.
that is the practical world application. What I'm asking is like, for example, I have this question in the exam
Hmm.
and I'm trying to solve this using this second notation. So,
Okay.
what should I take the value of k there?
What should you take the value of k here? Uh, okay. You can
Won't
take.
won't it be the minimum of m or n?
Yeah, it will be minimum of m and n.
Like that will be the maximum k can go, right?
Hmm. So maybe like if and all if it comes in the exam, you will have some options, right? You can check from there, like till where do you want to go.
Oh, okay.
Yeah. In general, you will take the minimum. So even let's say if the minimum is 4, then maybe sometimes till going till 2 or 3 can be sufficient. So can't say exactly.
Excuse me, ma'am.
Yeah.
Ma'am, quiz 2 questions are from week 5 to 8. Is
Quiz
it ma'am?
clusters from week 5 to 8. Yeah.
Yes, thank you.
So that was all we had for SVD. So from here now, Vishal will take over. So Vishal, are you there?
And yeah, so you want to take that week 8, right? So you can take that first and
Oh
then.
no, Ram is going to come. So
Okay, Ram will become.
yes,
Okay.
So everything will be covered today until week 8.
until week 8. Yes.
Okay.
Yeah. Okay. I will stop presenting.
Okay.
Yeah. Thank you all for joining.
Ma'am,
Thank you, ma'am.
these
Thank you
slides
very
are
much.
being
Thank you,
shared.
ma'am.
No, these slides are not being shared. We'll share it after the session.
Please share it, ma'am, because we have just one day. We need to revise it too.
Yes, just right after the session, we'll share it.
Okay.
Thanks.
Okay. Thank you.
Thank you, ma'am.
Okay. Yeah. So 1 second, I'll just set up my.
So you are going to take week 7?
Yeah.
Week 7. So there is one question in tutorial. Two questions were discussed in the tutorial.
Hmm.
each question step. If you could discuss that question as well, sir, or
Okay,
start
I'll
from that
discuss.
question.
Week 7, right?
Yeah,
Okay, so first we'll go
principal
to
component analysis.
and week 6 remaining portions. Those are not that difficult. Just I'll be just going through each and every topics in a while. So I'll just start sharing the screen. So those are like positive, definite. So there can be some problem from these portions in your quiz also, regarding maybe you can have some matrix and then you'll be asked to you'll be asked regarding the character of this matrix or how it will behave. Okay, or maybe you can have a function also, quadratic function, and there you'll be asked to know regarding the behavior of the matrices corresponding to that function. Okay, so I told you in the starting. So how generally you do that? Like if you have a simple quadratic equation, how generally you try to get the information regarding the matrix corresponding to that function. So can somebody tell me how generally you go for that? So that's a
Sir,
very
we first of all we write the Hessian matrix.
Hessian matrix.
okay. So you know how to write that, right?
Yeah, ffx first derivative and then take the second derivative with respect to x, y, z, like this.
Yeah.
Depending
So this
upon
is the
whether
one
we
of
are
the
getting 2
simplest.
cross 2 or 3.
Yeah, correct. So that's the one way to go. So, and this is the one of the best method also. So whenever you have anything, even if you have the matrix, you can directly calculate the eigenvalues and then can
We can use a greater than 0, bc minus ac minus b square.
that method is also fine. That is also fine. But if you have like 2 cross 2 matrices, then that method can be used. Okay, but if you have 3 cross 3 matrix, then that will become a bit hectic.
Yeah,
In
then
that case,
Hessian matrix would really help in that case.
In that case, we can do differentiate, sir, if fx's.
Sir, can you take an example for
Okay,
3 cross
let's start with that. And these are the slides, and whatever I'm using is like is used in the tutorial, I guess. Okay, so I'll be using the same slide, and wherever you have a doubt, you can just ask me. I'll just start with the quadratic equation, basic quadratic equation. Okay, some sort of written things also, that also will be shared, I guess, in the after this session. But first of all, we'll just go through the basic understanding of this concept, and then the example. The example is also been given here. Okay, so this is the basic function. This is the function that is like in the form of quadratic. How generally you write. So if you will compare, you will be getting a, b, c, d. See, even if this function, if you are calculating the Hessian matrix, okay, how will you do that? If you will calculate, so the behavior of this function, you will be getting similar to this one. So okay, so tell me the values of the Hessian matrices. What would be the value here? So what is fxx?
fxx. This is xy.
fxy,
And this is
fxy,
symmetric matrix, so you'll be getting same.
FY.
Okay, so what is the value you'll be getting? fxx, what is the value here?
So for quadratic, I think instead of Hessian, we can just stop with this ABC, right?
I will not be get. Okay, so a, b, c, so you'll be getting here 2a, right?
No, sir.
Yes.
Depending on the functions, sir, like what?
So this function, I'm just talking about this function. You'll be getting 2a right here.
Yes, sir.
Yes.
Okay,
right?
and you'll be getting here 2b, and this is symmetric. Every time you'll be getting symmetric. So the first and foremost thing is, if you been asked anything about the matrix that is not symmetric, you can't say okay about the how the function, this matrix or the function will behave. Okay, so the first and the foremost criteria is, and that is important, is that that matrix should be symmetric. Okay, and then only you can say anything about that. So if you are getting 2b here, should be 2b here also, and then you'll be getting 2c. So you can see that both the matrix will behave similarly. Okay, so I told you in the starting itself, the Hessian matrix not exactly replicate, but the character whatever you will be getting from this matrix will be similar to this matrix. Okay,
So
yeah.
So for all the convex functions, the matrix will be Hessian matrix will be symmetric.
Yeah, for all the convex, yeah, that's correct. So for all the convex function, you'll be getting the symmetric matrices. Okay, that's why generally we use the gradient descent whenever we have the convex function or the convex function. Okay, so this is what I told you. So if you are getting any functions in the exam and you've been asked anything, you can just calculate, write the Hessian matrix, and then can calculate, and from there you can use the method like maybe the eigenvalues method, or maybe you can see whether that how that determinant is behaving. Okay,
So
so that is a
Hessian matrix is symmetric for convex functions.
correct.
So, so actually, convex is, I think discussing the convex function is slightly like diverging, I would say, because it's in the ninth week. So, so I
Huh.
don't think,
So
yeah.
yeah, the convex function question won't be there, but
Yeah. So we'll
so
not
that
discuss that side. It's like,
we'll not discuss the
yes,
convex
sir. No,
function
sir.
per se.
Yes, sir.
Okay. So this was our function, the basic function, and we can see this in the form of the quadratic form, and this is the notation that those are not that important for your papers. Okay. And then so you can have a questions, you can have any like type of function and can be asked to calculate at which point the stationary point happens. Okay. So how will you do that? If you have been given a question in a function and then you have been asked to calculate the stationary point, how will you calculate that?
Partial derivative equal to 0.
Okay, yeah. So you'll be calculating the partial derivative with respect to, like, if you have the function in like two variables, so you'll be differentiating with respect to each variable and then you get it to 0 and then you'll be getting some values, right? So you'll be differentiating with respect to x and then with respect to y and equate it to 0. You'll be having the equation in the form of, you'll be having two variable and two equations, and then you can solve and you can get the value of x and y, because here the variable are x and y, right? Is it clear?
So can we just say gradient will be 0, the gradient vector?
Gradient will be 0. Yeah, correct. Gradient with respect to, yeah, gradient will be 0 for sure. But I'm just calculating. How will you calculate? That is what I'm saying. But the gradient will be 0 with, yeah. So that's why at the stationary point the gradient will be 0. That's why we are equating it to 0, right? And then we are solving the equation. Okay.
Yes, sir. Yes, sir.
So, and this is what, and then if you like need to know whether that stationary point is behaving like a maxima and minima, then there's another step. Like if you'll, okay, I'll let you know about that. So this is the second derivative. How will you do that? This is fine. And then you have, okay, yeah, and this is the four, what you can say, things like if you have the minima, like you have calculated the stationary point, okay, and then if you want to know whether that point, if you have been asked whether that point, stationary point, is, how does that behave, whether it's a minima or maxima, then you need to check this function. These are the conditions that you need to check. Okay, so you should be having in your mind, how will you know if you are able to calculate the stationary point for any example, and then asked regarding how does that stationary point will behave, whether it's a maxima or minima, then this condition you can satisfy. So you just have to do the partial in the quadratic equation. Also, what you were doing, whenever you have the station, whenever you have a minima at that point, what generally you were doing, you were differentiating, double differentiate that function and check whether that's, if at that point the function is double derivative is positive, then that point would be minima, right? And if that is, the double derivative is like less than 0, then that's a maxima, right? So in the earlier classes, maybe in the lower classes, you would have read about that. So here also, if you have the stationary point as minima, so this the fxx or whatever the condition has been given should be greater than 0, and that will be a maxima, a minima point. And if you have fxx less than 0, that's a minima point. And the other condition that you need to check, that this should always be positive. Okay, is this clear till now?
Yes, sir. So there's one
Sir,
doubt.
P comma Q is the stationary point, right? P comma Q.
Which one? Yeah. P comma Q is the stationary point.
So one doubt here is like when we are talking about functions in with three variables, or let's say like we have 3 by 3 matrix. So for the determinant, the same thing can be extrapolated, right? Like in the sense, Hessian matrix, 3 by 3 Hessian matrix.
So for the Hessian matrix for 3 cross 3, you'll be calculating like this.
Yes, sir. So you'll have to find out the determinant, right, and apply this.
Yeah, it should be like fxx, and you can write it like this.
Yes.
If this is in the three variable
Okay.
x, y, z, okay,
Okay.
and you'll be having fxy and fxzx, and it will be similar fyx, and it will be fyy,
Y is
fzy, and then you'll be having f of zx, f of yz, and then f of z square, okay, or zz, whatever you want to write, okay. So that will be your Hessian matrix for that.
So then, how
and
to
then
get the
we get the
equation from
determinant
this?
of this. We'll get the determinant of this and then proceed further. Like
Yeah, so for the 3x3, it won't be asked. Okay, so because in the lectures also it has not been like taught about the 3x3 matrices. Okay, you'll not be getting, because here it will be very difficult to calculate determinant, and then it will be really difficult for you to calculate in
so, but the
that
process
one.
is the same to after you find out the
The
determinant.
process will be the condition will be same every time.
Okay.
And so, how to find the equation from that matrix?
Okay, so from that matrix, the equation you can find it like, see, so from the option you can do, that's the one method, and the other method can be if you have been given the matrices. Okay, so by comparing you can do, like for example here it is one matrices, okay, and if you have been given like you were asking, you have been given the matrices and then you need to know regarding the function, right? This is what you are asking. Hello.
Yes, sir.
Okay, so you have been given the matrix, like for
Sir,
example
can you
1
check,
2 3 4. Okay, so
1,
what
2,
you'll be
3,
doing,
4, 5,
you'll be
6.
comparing with the
For
5
3
6.
cross 3.
Okay, so your matrix
7 8.
Okay, for 3 cross 3. Okay, so what you will be doing, one thing, see, you can, so that's a very lengthy method. The other method are also there. From the option you can eliminate the options and can get the right answer, but the basic approach is like you need to write A, B, C, and like a symmetric matrix, okay, and then see if you have like 3 cross 3 matrices in the form, the values has been given here, so you need to compare the values. So you will be getting a standard function, right? You'll be getting a standard function x, y, z, correct?
Yes.
From here you'll be, if you are writing A, B, C, like here also B, so symmetric as corresponding to that, you can write it D and A, or then here it should be C,
E,
and E, and then F. Okay, so you will be writing this matrix, so you'll be getting a function corresponding to this, right? You will be writing x, y, z, and then multiply with x, y, z. So you'll be getting a standard function, correct?
Yes, sir.
And that you need to compare with the matrix that you have got.
Okay.
And then you will be getting the values. So that's the one where that is very lengthy to compare and then get the values. The other method can be like, for example, in the C.
So, but there's
Sir, we
there's
can
one
skip
that-
it if it's
so
not
that's one-
important.
It's not. So
No,
see.
it could. So I think there's one method where see, diagonals will be the coefficients of x and y, x, y.
From the options you can get, right?
Yes,
See,
but the
if you
options
have
will
been
be-
function like, for example, x square plus y square, and the z square is not there. Okay, if you don't have the z square and the 2xy and then 2yz, so you can see that if you don't have the z square, that means this value should be 0, right? At this point.
Yes, sir.
Okay, if you have 3 cross 3 matrix, this, so you can choose the options wherever the 0, this z square is 0, right?
Okay.
Correct. And if you have 2xy, okay, so you need to check where is xy. So xy should be here and 1xy should be here, right?
Yes.
So that is how it's coming as 2xy.
Yes, sir, they
So this
have to
trick you
add up
can
to
use
the
to solve the
coefficient
problem.
like that.
What?
They need to add up to the coefficient x, y, y, z, and z, x. And all.
You need to check the coefficient of each the variable and then can predict from the options. Okay, that is the one way. And the other method I told you by comparing, but that is a bit lengthier method to do that.
Okay. Okay, sir. Thank you.
So most probably you'll not be getting the question. If you are getting the question, you can do it from the options itself. Okay, so don't worry about that. So the option will be created such that you are able to solve, because it's not like, because if you are doing in a basic approach like comparing each and everything, it will take like 10 minutes for each one question.
Okay.
So we have done that, and the most important thing is, so these are okay, fine, but the most important thing is from here. Okay, so you can be given like a matrix or maybe a function, and then you need to you'll be asked to know and tell the character of that matrices. Okay, so for example, if you have any matrices, here it's not been given. Okay. Okay, so for the positive definite matrices, as you know, how does that positive definite or positive semi-definite is generally like? Do you know about how does that curve look like? Positive definite and positive semi-definite, or maybe the negative definite. Okay, so this is how I will. Then if we go,
The positive definite is always above the
yeah, correct. Like it's like a, what you can say, it's a ball and that is upward, going upward.
Ball on the positive side only.
Yeah, correct. And the positive semi-definite is like a simple valley or a inverted mountain, you can say. Not a mountain, it's a valley where you can go. So I can't find any image from here. There's no.
I think you can search by graph.
No, it's like, okay.
Excuse me, sir.
Yeah.
Sir, I just want to take you back a little bit. Sir, sir,
Yeah, go ahead.
representing in 3x3 matrix, like a equation is given. Can you just show an example like how we do it? Like
Okay,
there was a graded assignment question.
Okay,
from
I'll
which
just open that same question itself. Okay.
Yes,
I
yes.
was having that. So you can see this. This is a definite, positive definite, and if the negative definite would be like you can just reverse that. Okay, that should be going downward. Semi-definite is like I told you, like a value, and this is a indefinite. Indefinite, for the indefinite, you can't say anything whether it will go up and down. Okay, so for the definite matrix, this stationary point will behave like a minima. Okay, and the reverse for the negative definite. Okay, so I'll just open the question you told, right? Okay, 6th week, that is 6th week, right?
Yes, in the 6th week. Like there are two questions, both are similar ones, so you can take
Okay,
any.
so this is what you're asking. See, you can see here. So here, this is represented. So you need to know regarding the matrix corresponding to this function. Okay. So I told you here, you can't find y square, right? So y square is not there. That means what? So your the center part should be must be 0, and you can see that from the 4 option, this is the only option where you can see that the coefficient of y square is 0, right?
Sir, basically the diagonal elements are x square, y square, and z square.
Correct, correct. If you will write it also, if you are multiplying this x, y, z, if you will multiply this, see how generally do the matrix multiplication. If you will multiply this x cross 1 and this x will be multiplied. So x square should be there, right? So x square, the coefficient is 1. That is fine. Y this. The coefficient should be what? Here the coefficient is y square, but here it should be 0. But z square should be minus z square. That is fine. And from 2yz also you can see that yz would, where the yz you will be finding yz. So here it is x square, it is xy, this is xz, right? So where you can find yz would be here, right? Are you able to see that? Yz would be here, because here if you will write it x, y, z, and if you're writing x, y, z, here it should be yz, right? And yz, the function should be 1, 1. So this should be 1 and this should be 1. Fine. That is how you'll be writing 1 plus 1 yz should be 2 yz.
Yes, sir.
So you can see that here it is 0. So this should not be correct. Similarly, here also 0 is there, 0, and there here only you can find it 1 plus 1, that is 2 yz. Right? So this is how you should be approaching this type of question. If you have been given a function and you need to write the matrix.
But y square is not given, no, sir.
Then
Huh,
that
y
is
square
zero.
is not given, right? That is why here the y square is 0. The coefficient of y square.
So in a way, the
Then what about xy also, sir? Xy is also not given, but they have written here 1 minus 1. So we have to calculate in the way that it should be
Cancel out.
0.
It gets cancelled out
Cancel,
1
That's
and 1.
why we
cancel.
have to.
That's why it
Okay,
becomes 0.
okay, sir.
sir, so the diagonal entries are representing the coefficients of these square terms, right?
Yeah. It will multiply, as you can see that the diagonal element will be telling you the x square, the coefficient of x square, y square, and z square. Okay. Okay, so I'll be moving forward.
Yes, sir, got it.
Is this clear? Okay, so I'll just go ahead. So where is that? Piece we were discussing. Okay, so this is what we were discussing. Okay, so for the positive definite, if you have, so I told you from the starting itself, you just have to do two steps. If you have been given function, calculate the Hessian matrix. If you have been given the matrix itself, you don't have to do anything. You just have to calculate the eigenvalues. Okay, if you are able to calculate the eigenvalues, just check the character of the eigenvalues. If all are positive, you can directly say it's a positive definite. If all are non-negative means if some lambdas are 0 and some are positive, then you can say it's a positive semi-definite. And similarly for the all other cases. Okay, mostly it will be asked regarding positive definite. So the starting four will be asked. Okay, mostly the positive definite or maybe positive semi-definite, negative definite, and negative semi-definite. Okay, so you can choose like do that for the so you just have to see this method only. There are other methods also, but now we should not be considering the other method. Just calculate the eigenvalues and see which type of matrix is that. For 2 cross 2, you can do that. Like for 2 cross 2, you can just check this value. If this is positive, you just check the determinant. If that is also positive, you can directly say it's a positive definite matrix. Okay. Yeah. So somebody is asking something.
So could you repeat the last one?
Okay, repeat. So if you have 2 cross 2 matrix like 1, 2, 3, 4, you will be checking this one, the first 1 cross 1 term. And if this is positive, you need to check the determinant. If that determinant is also positive, you can directly say it's a positive definite. Like here, it is 4 minus 6. So this is negative. So it's not a positive definite. Correct? Okay, I'll say it again. If you have a matrix A, B, C, D, okay, you need to check for 2 cross 2. I'm saying for 3 cross 2 also, 3 cross 3 also it is applicable. But again, for 3 cross 3, you need to check so many other steps also. Like for 3 cross 3, you need to check whether this positive, this is positive. You need to check 2 cross 2 term. If that is also positive, then you need to check 3 cross 3. So you need to calculate the determinant and then the determinant of 2 cross 2 and then the determinant of 1 cross 1. So basically the determinant of 1 cross 1 would be the same value. Okay, so generally we are just checking the determinant of each of the matrices that can be formed, the square matrices that can be formed out of that. Okay,
They
so here
should
also
all be greater than 0.
so if the A is positive, and then you need to see whether AD minus BC is positive or not. If that is positive, then you can directly say it's a positive definite. Okay, that is applicable for all the matrices, but for 2 cross 2 you can directly calculate.
So
Yes,
suppose if
for 3 cross
eigenvalues
3.
are 0 and 2, then it is semi-definite, sir.
Eigenvalues 0 and 2. Yeah, this is semi-definite, positive semi-definite.
Okay. Okay, sir. Got it.
Okay.
Likewise,
just
0 and minus 2, it is negative.
The best way is to calculate the eigenvalues,
Yeah,
right?
the best way is to calculate. So if you are getting confused, just calculate the eigenvalues and see. Okay.
so just to clarify, what you said was instead of finding the X transpose AX, we can just find the Hessian matrix and check whether it is positive, semi-definite, or definite.
Yeah, correct. You can do it with this term also X transpose, and then see whether this is behaving for all the functions of value, all the values of X, this is greater than 0 or not. So this is simply the energy that is conserved by that function. Okay, if that is the energy conserved by that function is greater than 0, then that function is a positive definite. Okay, basically that this statement means that, but that is very difficult to check. Like if you are able to, you need to check all the values of X, right? So it's better to go with this eigenvalues method.
So my question was, instead of A, for example, if the Hessian matrix is H, if we find whether the Hessian matrix itself is positive definite or semi-definite or negative definite or negative semi-definite, we can correspond that with the function itself. Is that?
You can. That is what I'm telling. Yeah, so you can tell about the character of that matrices also, corresponding to this the character of the function corresponding to that Hessian matrix also.
Got
You
it. Thank
saying for positive definite, the fxx term should be positive and the
So
determinant
for
should
the,
be greater than 0. What
yeah,
about
this should be,
positive semi-definite?
okay, so this should be greater than 0 and then fxy and then fxy, fyy, right? So this should be 0 and then the determinant that you will be getting, that should also be 0. And for the other cases, here it has been written here, right? Not here, I guess somewhere it is written. Yeah, here it is written. For the positive definite, this is written. This is the determinant itself, right? This is what this is determinant. If you have A, B, C, this will be B only, and this is C. So determinant is what? AC minus B square is determinant,
Yes.
and A should be greater than 0. This is what I was telling.
Okay. So this
Right?
table gives us the
Hmm.
based on the Hessian matrix term.
Okay. So
Sir,
this is
would you
clear.
be uploading this recording immediately after this session?
I'll try to do that. Okay.
Sir, please do. We
Okay.
have hardly 1 day between our exam.
Okay,
Sir,
I'll
I
do
have
that.
a question for 3 cross 3, sir.
3 cross 3. Okay.
Yeah, so just clear if my understanding is correct. First, we should check the uh, first row, first element is positive, and then matrix of the 2 cross 2. I mean, determinant of the 2 cross 2, and then go with the second row, second element, and then check the 1 cross 1. Is that correct, sir?
Yeah, correct. So
If
if
all are
this is
positive,
A,
it is
B, C,
positive. Definitely.
if this is B and this is D, so you need to check first A should be positive, and then this AD minus B square should be positive. Okay, and then you need to check the determinant of whole 3 cross 3. That should be, if all the 3 are positive, then you can say about the positive definite.
So
Okay,
this
and if you are anything, if you are getting stuck, like the center one becomes negative or any other things, then again you should be going and calculate the eigenvalue. So it's better to calculate the eigenvalues and then say anything about that. Okay,
so if we
yeah.
have been given a function in 3 variables and the matrix is not given, can you tell us how to populate the matrix using the function?
Okay, so this is what I was telling. So the method is to compare the value. Like you have some standard equation, right? How will you get the standard equation? So you
I
have
think
to
I
write this
understand.
n matrix and then multiply with xyz and this xyz. So
Right.
you'll be having a what you can say the standard function, and that you need to compare with the function whatever is given and whatever the value you are getting for ABC, whatever you are writing here, and then you can write the matrix. That's the one way. Okay, and that's the lengthiest way. The other method is to see the coefficient. So if you have been given, if you have been asked to the function has been given, and then you have been asked to calculate the matrices, right? So the Hessian matrix is not the exact same matrices that will be given. Okay. Okay, but the Hessian matrix can tell you the character, but not the exact same matrix. So what you will be doing is to see the function's coefficient. Okay, because this the first term will represent what, the coefficient of x square, right? If you have been given the function as x square plus z square, and the z square is not given, so the coefficient is 0 for this. So
Right.
here it should be 0, right? So
But
this
that will only tell us the diagonal elements. What about the non-diagonal?
okay, so the other method, like see 2xy is given. So because you'll be getting a symmetric matrix, so xy here should be xy and here also it should be xy. The coefficient, so you can write it xy. The coefficient should be 1 and 1. Right?
How do we know that it will always be symmetric? I mean, there can
Because
be.
we are talking about the symmetric matrices itself. Okay, here.
There are examples in a graded assignment. I guess.
Yeah, I got your point. So, but then again, you need to go and can. So that is what I was telling. It will not work every time. It will not work every time. The only approach is to then compare the values. Okay, from the Hessian you can't get, and this method, if this is not applicable, then it's difficult
Can we
to
do this
get.
in that xy, irrespective of whatever the coefficients are, they add up to 2xy? Is this valid?
See, why I wrote like this, because if I'm multiplying this x, y, z to some matrices, whatever the matrices the function will give us, and then x, y, z, so I'll be getting the same value from here, okay, and same value from here. That is why I'm just dividing it by 2 and then writing it here 1 1.
That works when the matrix is symmetric.
Symmetric.
If not, then we are out in
Then
the
yeah, so
0 2 or 2 0 also.
Correct. Yeah, it can be 2-0 also, but mostly it will be. It's not like hard and fast rule, but mostly it will be symmetric. Yeah, you can say that in the graded that's not the symmetric matrix, but in the graded you can directly solve with the, I guess, the coefficient of z square or
Yeah,
maybe
that
some
is
like
clear
that.
from the option only because the
So yeah, if you are getting this type of question, I guess the problem whoever has all said, I guess he would have taken
oh.
care of this options also.
Also, sir, since we are on the topic of symmetric matrix, this eigenvalue rule of all positive, does it apply to symmetric matrix only or all matrices also?
No, not for other matrices.
Yeah, only for symmetric, right?
Only for symmetric. If we have not given the symmetric matrices, then you need to mark like none of the
So
other
it is
matrices.
possible that a positive definite matrix has not negative eigenvalues if it is not symmetric, right?
Yeah, it can happen, but
Okay.
because we are just talking about symmetric, for non-symmetric we are not talking, so it can happen.
Okay. Yeah, thank you.
Sir, could you give me example of
Sir,
your
let us move next to the
Okay,
topic.
I'll just go next. So this is done, I guess. Okay, so this topic, I guess, is done. The positive difference, I don't think so there will be any problem. So I told you the basic approach is to, if you have been given the function, calculate the matrices. If you have been given the matrix itself, you can just directly calculate the eigenvalues. If you have been asked regarding the stationary point, you already know partially differentiate with respect to each and every variable and then equate it to 0 and solve the equation. You can get the stationary point. And if you need to know regarding whether it's a minima and maxima, there's a that approach also I told you. Okay, you need to double differentiate and get the values and can see whether it's a maximum and minima. Okay, this is a one example, this simple example, and then I don't think so that there is this you can solve with the C. If you are calculating the Hessian matching, what would be the value you will be getting?
Hello.
Okay, tell me that here.
XX.
Okay, XX, but what the exact value you will be getting?
2 into 2.
4, 8, sir.
It should be 8 here, right? And here it should be 4, and here it should be 4 and 4, right?
No, it should be 2, no, sir. X in the place of XY. 2, no,
No,
sir.
if you are differentiating, you will be getting 4x, and then differentiate, you will be getting 4.
Okay.
Okay, if you are differentiating 4xy with respect to x, what you will be getting? 4y.
Yes, 4.
And if you are
Sir, 4.
differentiating with respect to y, you will be getting 4, correct? So
Yes,
4,
sir.
if you are getting here, it will be, you will be having 4 here because like always it's a symmetric matrix. And then, so the behavior, what should be this matrix be like? So whether it's a positive definite or positive semi-definite or negative definite.
Positive definite.
Should be positive.
Okay, so because 8 is positive, and if you are seeing this one, 8 into 4 minus 16 is positive. So it's a positive definite, right? So this way, if you have been given 2 cross 2, you can directly say. Okay. So what about the, and you can check for the station. Okay, tell me the stationary point for this matrices. Just, it will not take more than 20 seconds to solve this. Okay, solve this and tell me the stationary point. So what you have to do, you have to differentiate with respect to fx, equate it to 0, differentiate with respect to fy and equate it to 0. You will get the value. So what the value you are getting?
Is it 0?
0, 0. Okay, and that will be a minimum, right? If
That's
whatever
what
the stationary point you are getting, PQ, that will be minima. Why that is minima? Can somebody tell me why that is minima? Without doing the partial
All are positive, sir.
fxx is
All are
greater than 0.
Okay, it's a positive definite matrix, right?
That is 4. Yep.
Positive definite, that means it should be something like that. Okay, and that so that the stationary point always be a minima. Okay, this way you can say regarding the minima maximum point also. Okay, if you have been asked to know regarding the stationary point, the behavior of the stationary point from the character of the function, you can directly say. Okay, so this way you can do that. And so this is the plot of that function. You can check with respect to determinant also. The determinant, okay, the determinant method I already told you. You can do with the eigenvalue test also. You can calculate the eigenvalues. You can see that the eigenvalues are positive, so it's a positive definite. Okay, this is the other way to solve this.
Sir, here the eigenvalues, we have to look into only the real values, whether it is positive or negative. Because 3 minus root 5 and 3 minus root 5, is it
Both are
positive, sir?
positive, right? Both are positive.
So determinant is an easy way of checking it, because if we calculate eigenvalues, so that will take some time.
Okay.
Yeah, for 2 cross 2 you can do that. Yeah, this even
Sir,
for
can
3
you
cross 2 you can do, but if
teach
you're not, yeah, go ahead.
can you teach us how to do it using pivots? That will be easier, I guess.
The pivot is okay. So that also you can do that pivot values, but again you need to, okay, so what you're asking, okay, whether this one determinant test or pivot, again you need to, what you have to do, you can okay, so 1 cross 1 you have calculated, you can calculate for 2 cross 2 and then divide it with the determinant that you are getting for 1 cross 1, okay, and again for the 3 cross 3 and divide it, so whatever the value determinant you are getting, divided with the determinant of the 2 cross 2, and that should also be so okay. So there are other methods also, pivot test is also there, but it's better I'm telling you to go with a eigenvalues test. Okay, see why I'm doing why I'm telling for the pivot test, if you, for one cases if you are getting negative, what do you do from there? Like for example, for 2 cross 2, if your the first determinant is negative, second determinant is also negative, right, and the third one you are getting, you'll be getting positive, right? See, and so you'll get, for sure you'll get confused that I tried this pivot test also, so I was getting confused somewhere, so that's why I just this method will work, but again you need to remember some other aspect also, like for example, if you are getting the pivot term, some pivot term, so even pivot term should be positive, so there are like some confusion, so that's why I just skip that method.
Sorry, one question in short. Suppose we
Yeah.
are given 3 cross 3 matrix.
Okay.
Then what should be the approach to test the positive definite function?
So it's, so the best method is to calculate the eigenvalues. Okay, but if you have been, so see, that depends on the how that matrix is. If you have been given the matrix that is very simple to calculate the eigenvalue, you can directly calculate. Like for example, if all the diagonal, only the all the other term are zero and only the diagonal values are there, like a, b, c, and all the a, b, c are positive, so you can directly say it's the eigenvalues only, other values are zero. So
Yeah, sir, right.
okay, that's the, but it depends on the matrix. Okay, if you have been given the matrices and you can see that this first term is positive and the second term is also positive, then you just have to calculate the determinant for the last test, right? The determinant for the 3 cross 3, and if that comes as positive, then you can directly say it's a positive definite. Okay, so there that method becomes very simple. But for for example, if you are getting for 2 cross 2 as negative or something zero, okay, then what you will be doing, you have to calculate the eigenvalues to check
Okay,
like
okay,
exact
sir.
how does that behave. Okay, this is what I was telling.
Okay, sir, got it, sir.
Hello, sir.
Yeah.
Yeah, sir. Could you please give me
This one is semi-definite, no, sir?
or
Sorry.
non-negative?
This is what, okay, tell me what is this? This is semi-definite. No, this is not semi-definite. So the eigenvalue, you can directly say it's the eigenvalue is what, 1 comma minus 1. So how come this is semi-definite?
Negative.
Infinite.
It is neither positive definite nor negative definite.
Oh, if we have both positive and negative, then it is inconclusive.
Yeah.
Okay, sir.
Okay, so I guess this week we are taking a lot of time. So this I told you, right? So this the problem from this portions can be solvable, right? And you'll not be getting that difficult question to solve this. Okay, so don't think much. So don't lose too much sleep over this portion. This is not that difficult to solve. Okay, you'll be able to solve this. So can we go to the 7th week?
Yes, sir.
Yes, sir.
Sir, for which question should we lose sleep?
Yes, sir.
Tell us the topic for which we should lose our sleep.
Okay, so okay, so this portion I told you. So I'm just telling you that this portion is not that difficult, like to solve in the exam. So the problem from this portion is mostly not that difficult. It's like it can be, you can solve this. Like I told you the method that always you'll be using. Okay, So you'll be getting this type of problem itself. So you'll be getting some matrices and then, or maybe the function. So you have some 3-4 questions from this week. So, and then there will be some questions like you can have functions and then you need to say about the stationary point, or maybe the which type of the stationary, how does that behave. So this type of questions only will be there. Okay.
Sir, from first 4 weeks, how much will
There
we
won't
be
be any
getting, sir?
questions. From first 4 week there won't be any questions. There can be questions to solve like maybe eigenvalues, eigenvector, but those are like in the week
Yeah,
7,
yeah,
6, 5,
yeah.
like everywhere. Okay. Okay, so week 6. Okay, so week 7 I'll not be discussing. Okay, so week 6, do I need to go through the like what does that PCA mean, and also or directly we can go to this
Sir, just go to the tutorial
So let's
question.
go on
First
the
question of the
questions
tutorial.
directly, because we are not getting some theory over there in exam.
Just go to the important
Yeah,
part.
the question, the
Important
kind
thing.
of questions we'll be getting in exam.
Yeah.
Okay, so from the PCA, you already know the theory behind the PCA, the basic theory. There can be some question regarding the concept from the PCA. So you know how does, like, why does the PCA used, where we are using the PCA, which type of the algorithm is this is and all you already know, right?
Yes, sir.
So I'm just telling you
Yeah,
this
gradient
statement.
descent.
So this is used for the visualization, because if for some bigger dimension I can't visualize, so I just need to reduce the dimension. Okay, so this is the one way. So this is the one benefit of the PCA. This is the unsupervised learning. Okay, that you have already read in the week 1. But if some statement can be
Sir,
there regarding the PCA, you need to correct that. And
one thing, this slide is not being shared though.
okay, I'll share this with after this session. Okay. So for the theory you can just go from like there is only 2 pages. You can just go through that. I'll just start discussing the problem. Okay, is that fine?
Yes, sir.
Okay.
Yes, sir.
Yeah, so the only thing is then what is the optimization problem for this cases you'll be getting with. So what you have to do here, you have been given a large chunk of like what you can say the dimension or the features, and from those features you are, so like from those features you need to, like, for example, you have 1,000 features in the starting, and then you need to reduce it to 4 or 5 dimension, because you just want to visualize those because you can't visualize for the 1,000 dimensions, so you just need to reduce it to the 5 dimensions. Okay, so how does it is done? Like, so here the optimization problem is you have to get some sort of direction. You just need some directions where like 5 out of that 1,000 features, you just need some 4 or 5 dimensions or the directions where the variance is maximized or the reconstruction error is minimized. So this is the optimization problem. If you have been asked to know regarding the optimization problem and the constant for the PCA problem, you will be able to do that, right? Correct. So there is so you can solve this PCA problem. The first option is while solving this PCA problem, while getting the direction where the variance is, you are maximizing the variance with the constant such that that vector should be unit vector. Okay, so what is here I am just writing it. So this is the constant, not the constant. This is the constant. Constant means what are the condition that you are applying on the vector. Okay, so what is the condition that you are applying? That vector should be unit. Okay, that should be a unit vector, correct? And what is the problem that you are solving? This is the optimization problem. So what is the optimization problem you are solving? You are just maximizing the variance. So this you are maximizing, and while maximizing the variance, you just want to get the direction. Okay, in which direction the variance is maximized. This is what you are solving for, and this is the constant problem. So if you have been asked to know regarding from the options which of the following generally tells you the optimization problem and the constant, so you can just mark the wherever the variance is getting maximized and the error is getting minimized, reconstruction error is getting minimized, those portions you can mark. The constant will always be same, because in each and every one the optimization problem can change, but the constant, that the condition that you are applying on the unit vector, will always be same. Okay, is this clear to everyone?
So can you please repeat one more time, sir?
Okay. So see, if you have been asked to know regarding which of the following options are the optimization problem and the constraint for the PCA, okay, principal component analysis. Okay, so
Okay, sir.
how we are solving this? What we are doing is from whatever the features we have, like here. So the basic example that I told you was here. So I have a ML model and I am just calculating the features for some thousand people from some village. Okay, and I need to predict what weight of the person. I need to predict the weight of the person, but I'm taking is the features that I'm collecting is the height and the blackness of the hair of the persons. Okay, for the 1,000 people.
Yes, sir.
Okay, while calculating, so you can see that the variation in the height is much larger than the variation in the blackness of the hair, because you can see whatever the feature that I've collected from the 1,000 people, the hair will always be mostly the black or gray, right? So if I'm just putting those black as a one, I'm just giving some values. So gray will be what, 0.98 or 0.98. Okay, so the spreadness or the variance in this feature, the blackness of the hair features, will be very small, and then the variance in the height will always be a very large, right? So this is what I was telling. If I need to predict the weight, so I can just skip the blackness of the hair, because whenever if for example this model was like this, m1 into x1 plus m2 into x2. Okay, and let's, for example, m1 is the coefficient regarding the height of the person, and m2 is m2 is the, what you can say, the coefficient regarding the blackness of the hair. Okay, and m2, you can see that x2 will always be same, right? Because you can see that the spread is very less. Spread is very less means what? So if the person is black hair or gray hair, so mostly like a black or the dark gray. So for example, for the black, I'm giving the mathematical value as 1. For the gray, I will be giving 0.98 or something like that. Okay. So every time the values is always same. So if the value is always same, this part will always be same. So this is not going to help me to predict the weight of the person. That's why I can just skip this. So this is what I'm just learning from this two features stuff, that if I have a features, so for those features I can just skip those features where the variance or the spreadness is very less. Okay, every
Yes,
time the
okay.
function's value is getting same. Okay, so this, I think so, is it clear?
Yes, sir. Yes, sir.
Hmm.
If variance is less, then we can leave that feature. Okay, sir.
Fine. Yeah. So this is not the exact thing that the PCA, how does that PCA, not exact replica of that. Okay, not the exact replica of how does that PCA work, but similarly it works similar to that. Okay. So here also I'm doing the same steps. I'm just maximizing I just want to solve this problem. I just want to maximize the variance. I just need a direction where the variance should be maximized. Okay, and I'm just trying to I'm applying some condition on the unit vector, that the unit vector, that vector should be unit. That is the constant of the optimization, and that can be solved with the other method also. And the other method is to minimize the reconstruction error. Okay, so this the true optimization problem can be there for the PCA. So this is, I get, and yeah, and whatever the direction you're getting, like for example, you're getting 4 direction, all the 4 should be perpendicular to each other. So mostly they are orthogonal to each other, right? Okay, and can somebody tell me when does the PCA won't work? So can be the limitation? So there can be some limitation of the PCA also, right? So okay, so just think for some like 1 minute and just tell me for what can be the limitation of the PCA.
Reduces quality.
What?
Reduces quality.
Pictures quality. This is what you're saying.
So when the spread of variance is not less for any for any feature, when there are no features where the spread of variance is less, so basically you're not reducing the dimension, because basically in the situation where the variance is not less for certain features, where all the features have high variance, high spread, maybe in that case there's no point in reducing dimensions.
See, this is what I was telling.
No, sir, it is non-linear data.
Yes, nonlinear data will be the example, I believe.
Yeah, that's correct. If you have the non-linear data now, there that the PCA won't work correct. Like it will work, but it's not the so not work that well. Okay, so that's the one limitation for the PCA. Correct? Did you get the point? If you have non-linear sort of data, so there the PCA won't work properly. That can be the one limitation. Okay.
Yes, sir.
Okay. So that was it. Okay. So the basic theory, I guess, is clear regarding the PCA. If you are getting any statement type of problem, like you can have like 5-6 statement regarding the PCA, and then you need to mark which of the following is the correct and all. So I guess now you'll be able to mark that.
So one question. So over here it is written like maximum UTC U. So can you discuss a bit about this?
Okay, so here see, so this is not this is similar to that see here the variance I need to maximize. So I'm taking the projection of all the data on the unit vector, right? And this is what the variance is. So the variance formula is this one, right? So you're just taking how that the data are from your the midpoint, right? So this is what I'm telling, and this can be written in this form also. How will you write that? 1 upon n summation of this, and if you are taking xi minus x bar ka transpose, and that square will become like this, like what you can generally write like the x transpose is what x square, right? So similarly it's written like this, and then you can write like this. This is the covariance matrix. This C is the covariance matrix, and you have U transpose and U. So if you have been given directly to maximize this is the variance, right? This is optimization problem itself. So the optimization problem can be written in this form, or maybe can be written in this form. So you can directly write, okay, this is the optimization problem. So this you have to maximize and get the U, and the constant is U transpose U equals to 1. That means that the vector should be unit. Okay, and how generally we get that? You can see it from here. I have just written it and then scanned. I don't know where I have written this. This is for the.
Can we solve one problem, sir?
Yeah. So the theory part is clear, right? Or it's not?
Yes, sir. It is.
So in other way, it depends on the question.
Sir, can you put a second on projection formula?
No, okay.
So let us do one example, sir. Then only it would be clear.
Okay, so and this also I'll be sharing, but you can just go through that. It's not much important, but only the steps has been written. How generally, so this I guess is not important for now to go through the how generally you get the how generally you solve that. Only what should be there. So the basic theory behind the PCA should be there in your mind, and how generally you solve any problem. Okay, so these are the steps. Okay, that is fine. I'll just go through the some problem you're saying. Yeah.
Can you go to that formula?
Okay.
That's projection formula. Yeah. So in this we have to use only one U.
See, so that's the confusion for so many people. So the problem can be like this. Okay, so there can be a problem where you can be given data will be given. Okay,
sir, can you take?
Okay, I'll take first. I'll just tell you, and then I have one problem. I'll just discuss the same problem. Okay. Okay. So the data will be given. You can directly calculate the steps. I'm just telling you the first step. The first step is the data has been given. Okay. The second step, you can just find the mean value, because mean will be required to calculate the covariance. What is the formula for covariance? This is the formula, right? 1 upon. So this is what I was telling. So somebody was asking regarding the covariance. This is what. So this is same thing, right? U transpose C U. Okay. So this is what the covariance is. What 1 upon n summation of 1 ka n. This is the covariance matrix. So for that you should be able to calculate the mean. First step is to calculate the mean. Then the covariance matrix, you can have the problem like the data can be given, and then you can be asked to calculate the covariance matrix, or maybe the eigenvalue corresponding to the covariance matrix, or maybe the eigenvector corresponding to the covariance matrix. Okay, and this is important that I'm telling you. to solve this type of problem. Okay, and then so the eigenvalues and the eigenvector, those are the some other step, and the projection data. Okay, so you have the doubt, I guess, in here somewhere. I guess in the tutorial it is written like this one, the first step, the first stem cell. That is not correct, because you need to take the consideration of the other step also. So what you are doing, you just have to take the projection of the data, okay, on the vector that you are taking. Like for example, you got eigenvector as 5 and 3 and 1. So this would be your first vector, right? This would be u1, and this would be u2, and this would be u3. Why is this the first vector? Because this is corresponding to your maximum eigen value. So this is your principal component, the first principal component, right? And this is the second and the third. Okay, correct? Is this clear till now? Okay.
Yes.
What you
Yes,
doing?
sir. Yes, sir. Till now it is clear.
Huh.
What about the second component, sir?
Okay, so the second component is what? Let's, for example, you just have to project the data points from 3 dimension to the 1 dimension. Okay, if you have to project the data from 3 dimension to the 1 dimension, so here you'll be, so the here will be j will be from where to where? J will be from 1 to 1 itself, correct? And here it will be from j equals to 2 to 3, right?
There will be no second principal component if m equals to 1, right? Because we are reducing it to 1.
You are reducing it to 1 dimension, that is fine, but you have to take the consideration of that
Correct,
vector
yes.
corresponding to this should be used here. You have to take the projection of all the data on this vector plus the projection of all the midpoint on other vectors also.
Exactly.
Okay, that you need to take into consideration. You can't just skip this. You can skip this whenever you have this u2 is perpendicular. So u2 is perpendicular to this x bar. If you are getting this one, or u3 is perpendicular to this x bar, you can just skip this. Or if you are getting the other condition is x bar is 0, that means 0 0 0 vector. So whatever the dimension is that. So if you are getting the mean vector as the 0 vector, or u2 is perpendicular to the x bar, or u3 is perpendicular to the x bar, then you can just skip this one. But if out of the two condition, if none of the condition is getting satisfied, then you can't skip this one. So this is what I was telling you from the starting. Yeah, and now you can ask you about.
This makes sense because this goes with the derivation which the professor told us. And
this is the, yeah. So I don't know, in the tutorial it is written incorrectly that I told you in the last session also, whenever I was taking the 7th.
Yes, sir. Yes, sir. You pointed out.
But
yeah, I told you in that session also.
Practice assignment, all the questions when you solve using X bar, right? Because that's what I was doing. Our answers do not match the option. For example, in graded assignment, if we solve the reconstruction error using X bar, I mean including X bar, the reconstruction error comes out to be 0, but 0 is not even in the option. Okay. Same goes for the practice assignment. So I have been asking
that
question.
Yeah. So that I pointed out at that time, one or two questions answer, the option even is not given there.
Oh.
Because I guess so. The question, I guess he has he has solved the problem corresponding to u2. Maybe he would have taken he has just taken the first term. I guess he has not taken into consideration the second term. But I'm telling you, if you are getting anything in the exam,
sir, we need this particular PDF step, sir, because if we go with that, we are getting error. So how can we get the PDF?
So I'll share this, all the PDF I'll share. So I have like 4.
So can I ask one question that here?
Available at in the
So what we will do, sir, in the examination?
Where do you access this one, sir? Which link?
Okay, I'll just upload it now itself, and then I'll share this the link. But this is within the lecture also. The same formula is there in the lecture also.
Right, in 7.2.
I think
the lecture
if we
is
solve the question, everything will be clear.
Going through the lecture, it's like I mean, now it's too late to go through the lectures. So I just
no. I'm not telling you that you have to go to the lecture. I'm just telling this is the formula. So this is the only step that is somewhere it is written incorrectly.
Sir, I have a question. If we center the data by subtracting the mean and then find the covariance matrix, then we can skip the second term in part 4, right?
But if your mean is 0, yeah, then you can skip that.
Because you centered the data, the mean will be 0, right?
Yeah. Then you can
so
skip
I
that.
think life will be easier if we just simply center the data.
but your other values will get changed, right?
Right.
Sorry?
Your other values would get changed if you are just centering the data.
Which ones?
Everything will get changed, because if you are just centering the data, that means what you are doing for every data point, you are changing something, right?
Yes.
Centering the data means what? You are just shifting all the data somewhere else.
By subtracting the mean.
So you are changing the data, right? So if you are changing the data, everything will change. Your final answer will be same, but the step will also be same. But every time you will get the different data out of, like if you are calculating with this approach or calculating with the approach that you have told.
But
So
our
one more
ultimate
doubt,
aim is to get the projected data point, that I will get the same, won't I?
Yeah, you'll be getting same, correct.
So I think I've achieved my purpose if I just need the projections. I
Yeah,
don't
yeah.
have to do the second term. Otherwise, I have to find the projection of the mean with each of these weight vectors.
But see, yeah, you are correct. But what I am telling you, in the exam, mostly you will be getting the problem where either the mean will get 0, or the vector like u2 and u3 will get be perpendicular to x bar. Okay, so if
Okay, so
out
we
of this
won't
two
have to do
condition,
anything. So we won't have to do the second term.
sir, moreover,
yeah.
sir, now we are reducing from 3 to 1. Suppose if we are reducing from 2 to 1, then the first term is enough, no, sir? Or 3 to 2, or 2 to
No,
1.
every time you have to, like for example, if you are calculating from 2 to 1, right?
Yes.
2 to 1
Yes,
means what? J will be from 1 to 1, that means one term, and J2 will be what? 2 to 2, right? So you have to consider this also.
sir,
Okay,
then can
I'll
you
just
please
take
solve
one
one
example.
example that to make it more
I'll just
clear?
take one example.
So
Okay.
PA
Yes.
question, sir. Practice
Yeah.
assignment question.
Okay,
Will
I'll
this
just take
formula
that.
be available in exam?
No,
Or
there
will
won't
it
be
have?
any formula in the exam. There won't be.
We need
So
to.
there's no there now. There won't be any confusion. I told you, you have to take every time here. This live, I guess the live session you haven't attended the last live session. So this is the formula that you have to use every time. There is only catch is if you are getting the first condition is if you are getting the mean as 0, then you can just skip this one directly.
Okay.
Or the second condition is your x bar should be perpendicular to all the other vector. X bar should be perpendicular to u2 and u3. Okay, all the other in spite of the principal component. If out of this two, if any of the one condition is getting satisfied, you can just skip the other part. But if this is not happening, you have to choose, like you have to take both the term into consideration. And this I have been telling you like repeatedly, like again and again
Can
from
you
the
take the
last.
example?
It's a PA question, sir. Practice assignment question.
Okay.
All about PA, sir. Please see only, sir.
So I'm just.
Sir, could you please share the mock solutions also?
Okay, mock solution is not shared to you.
No, sir.
Okay, I'll just ask to share that also. So, okay, 1 second. So, one questions I will solve, and then so if you are able to solve,
So
so
what will be the last day of submission of mock? Is there a deadline to submit?
mock submission, I don't think so. There is any
No, sir.
deadline.
It is only for practice. So that's why I
There
am
is,
saying
no
just share the
deadline.
solution, sir.
But actually, it's being considered in the graded assignment for bonus, so
Yeah.
that's why I got confused.
So mock
Before
is
quiz,
bonus, right?
before quiz,
Okay,
we
you can
need to
just
do.
submit it before maybe.
So you can click on submit button and check the answers. Not worry before quiz. Sir, can we go to the question, please?
Okay.
Yes, sir. Practice
So
assignments.
yeah, so you have one question. Okay. Here it is given, right? 0, 1, 1, and then okay. So you are getting this problem. So tell me the mean first. So that start the calculator. You can just this type problem can be there. Yeah, what 3 cross 3 you will not get. Maybe
One,
you can get
one, one, one.
1, 1, 1 you are getting. Okay, now tell me the covariance matrix. So I'm telling you all the steps. So the first step is what? Step 1. Calculate what? X bar. Step
Sir,
2 is what?
just do it a little slower, sir, so that we are able to just this one be the only example, and we would get all the points cleared.
Okay. So the first thing is what? The step 1, what generally you do. So start telling me also, like otherwise, like I'll be doing and again in the exam.
Mean
So
of the data, sir.
first step
Yes,
is
sir.
what?
Yes, sir. The mean vector would be 1, 1, 1.
Okay, so the first is what? X1 plus x2 plus x3 by 3, right? And if you are doing that, x bar is what? 1, 1, 1. So now you can see that x bar you are not getting mean, and x bar you are not getting 0. So the first condition is not satisfied. The other condition is left. So that is what, if the other vector, the vectors that you are getting is will get be perpendicular to this, then you can replace it. Okay. Okay. So what is the second step?
Covariance.
Okay. So this is the second step. Okay. Covariance matrix. What is the formula for that?
C equals to 1 by 2
x minus x bar and
x minus x bar into x
transpose.
xi minus
Transpose, right? And you have to do the summation from 1 to whatever it can do. Okay, so tell me the values, the direct matrix. Okay, calculate and tell me the covariance matrices.
Could you give us a minute, please?
What?
Could you give us a minute to do it?
Yeah, sure. You can just take your time and solve.
Can you show the matrix again?
Okay, I'll just show you the x is x1, x2, x3, right? X1 is what? 0, 1, 2. X3 is 2, 1, 0. And this is 1, 1, 1. And x bar you are getting 1, 1, 1.
So 2 by 3, 0 minus 2 by 3.
What you are getting?
2 by 3, 0 minus 2 by 3.
2 by 3,
0
minus 2 by 3.
0, 0, 0.
0, 0, 0.
Minus 2 by 3, 0, 2 by 3.
2 by 3, 0, 2 by 3. Okay, and while calculating the covariance matrices, this is the value you will be getting. Okay, everyone is getting the same value, right? If you are not getting, just tell me here. Otherwise,
Sir,
if you are doing a
do it,
mistake in the covariance matrices in the exam, that will be a blunder.
Sir, can you please do it here yourself so that we will get into no mistakes?
Okay. See, but this, I think so, this was solvable. I don't think so there was any problem. If you are just again asking me to calculate this and again the eigenvalues, you've already been solving the eigenvalues, eigenvector from the week 3 or week 2 itself. So this is the last thing that I'm solving. Okay. So this is the covariance matrix. We have to calculate what is the formula 1 upon n, right? And what you will be doing. So the first matrix what you will be getting is this x1 minus x bar. If we are doing x1 minus x bar, what the value will be getting? Minus 1, 0, 1, right? And if you have to multiply with minus 1, 0, 1, correct? This is 1 upon 3. Similarly, if you so this you have done, you got it right. So how you are doing? X minus x bar is there. So x1 minus x bar. X1 is what? 0, 1, 2 minus 1, 1, 1. So you'll be doing 0 minus 1 is minus 1, 1 minus 1 is 0, and then 2 minus 1 is 1. Okay. And similarly, you are doing for x2 minus x bar. X2 is what? 1, 1, 1. X bar is also 1, 1, 1. So you'll be getting 0, 0, 0. Similarly, 0, 0, 0. Right? And now for the third one, x3 minus x bar. That is what? X3 is what? 2, 1, 0. And minus of 1, 1, 1. So you'll be getting what? 1, 0, 1. Similarly, 1, 0, 1. Okay? Do the multiplication. And so you'll be able to do this, right? Multiplication. This is 3 cross 1. This is 1 cross 3. So this will be 3 cross 3. Similarly, this will be 3 cross 3. This will be 3 cross 3. So if
Sir,
you are
it
doing
would be last one, it would be 1 0 minus 1.
Yeah, 1 0 minus 1 I also got.
Yeah, 1 0 minus 1, that is fine. 0 minus 1 is minus 1.
Okay, then that will be 0 in A3, 1 3. Hello?
Yeah. So you have got the correct, right? The covariance matrix you are getting similar to like this.
Sir, then it will be 0, na?
1 0?
1 3.
1 0 0. 1 0?
Third element.
Here.
Not that. First row, third column.
This one?
Yeah, that will be 0, right?
Okay, so this is minus 1. Okay, no. This is -1 now.
So that is correct.
No, it should not be -1 and then -1. This is -2 and then we have 1/3. So -2 into 1/3. So this should be -2/3. Got it? See, -1 into 1. Right?
Okay.
So it should be -1 from here. From here it is 0. From 1 minus 1 into -1.
Yes,
So
sir.
-1, -1, -2, and then multiplied with 1/3. This should be -2/3. Right?
I got it, sir.
And now calculate the eigenvalues, eigenvector and eigenvalues for this matrices. I can directly calculate from here, but you need to calculate in the exam. I can directly calculate from here.
4/3, 0, 0.
Yes,
4
sir.
by 3.
4/3, 0, 0.
Okay, and the eigenvector?
So how to do it directly, sir? It's faster way.
I'm using the PC, like maybe in the exam. The eigenvalues, like you have to calculate from the basic approach, right?
So
Okay,
that
tell me the value.
higher order equation, no? Like let us say if it is alpha cube
0
plus alpha square plus
minus
alpha,
2/3.
it becomes easy to calculate the eigen values, but when it becomes higher order like alpha 4 and alpha 3, alpha that becomes little difficult. Could you give an example in that? How do we get the eigen value there?
So you just so there is no simple way to solve this.
No. If it is alpha cube plus alpha square plus alpha,
then you just
so
have to get one alpha and then
easy. But
you...
when it becomes higher order like alpha 4, then alpha cube plus alpha 2, then alpha, that becomes a little difficult to find it out.
Yeah, that will be a tougher to solve. Yeah, correct.
And even
there is no any...
graded assignment also, one question was there regarding.
But there won't be any question in the exam for that. I can assure you. Because that will become difficult to solve, right?
Yes,
so you don't have 1 hour exam, and if you have 16 questions, you can't solve like the problem if you're taking like 5-7 minutes for one question. What is the value here?
Minus 2/3.
Yeah, 2/3.
0, 2/3.
2/3. Okay, so what is the value you are getting? You are getting 4/3, right?
Yes, sir.
Okay, not that is the trace. What is the okay? So the eigenvalue you are getting 4/3, 0, 0. Fine.
Yes, sir.
Okay, so you are getting eigenvalues λ1 equals to 4/3, λ2 equals to 0, and lambda. Okay, tell me what is the principal component? Okay, I'm just taking the two principal component. So what would be the value for the projection variance?
4/3.
Okay, if I am having λ1 equals to 1, λ2 equals to 2, and λ3 equals to 3, what is the projection variance if I am taking direction as the principal component? Two principal component if I am taking, what is the projection variance?
5.
5.
Okay, 5. If I am taking only one projection variance, that is the
3.
Then the projection variance would be 3. And if I am not talking about the principal component, then total projection variance would be what? 6.
6. Yeah.
How are we arriving at this?
What?
How are we
Okay,
arriving at
and this
this?
is important. That's why I'm telling you again, if you have been given, like for example, you have the 3 dimension, and from the 3 dimension you will be getting 3 lambda or the eigenvalues, like lambda equals to 1 equal, let's for example you are getting this 1, 2, 3 value. So your principal, the first one would be 3. So you must be if you have been asked to convert from 3 to 1 dimension, you will be taking into consideration taking the eigenvector corresponding to this eigenvalue, right? And then this one, and then this one. Okay, so the first principal component
decreasing order, right?
Yeah, in the decreasing order. So the λ3 is greater than λ2 is greater than λ1.
Yes.
If you have been asked to calculate the projection variance, projected variance, just you've been not told anything about the principal component, just been asked to calculate projected variance, what you'll be doing? You'll be doing λ1 plus λ2 plus λ3. Right? Fine.
Yes.
Or if you have been asked to calculate for the two principal if you've been taking into consideration two principal
Projection
components.
variance would be 1 plus 2 plus 3.
Yeah, for projected variance is 1 plus 2 plus 3. But if you have been asked to calculate for the two principal component, what you will be doing? Now, what is the projected variance? If you are just taking into consideration two two principal component, what should be the value now?
3 plus 2.
3 plus 2. So, okay, that is fine. So, you can do this. If you have been asked to calculate how much percentage of information is conserved if I'm converting from 3 to 1 dimension, what is the percentage of information that has been conserved if I'm converting from 3 to 1 dimension? What should be the value?
20%, 50%, 50%.
This would be 3 upon 3 plus 2 plus 1. That is
So,
50%.
What, sir?
So how much percentage of information is conserved if I'm converting from 3 dimension to 1 dimension, the P shape? So the information that is conserved is how much? 50%. Okay, and I'm losing also 50%.
In every case?
Not in every case here, because the lambda 3 upon lambda 1 plus lambda 2 plus lambda 3. Okay, if you have been asked to calculate from 3 to 2 dimension, if I'm changing, how much information I'm losing? What should be the value?
Okay.
1 by 6.
5 by 6.
Okay, that should be 1 upon 6, I guess. Yeah, 1 upon 6 is correct. So here, from here, you'll be getting 2 upon
Sorry,
3.
the question was how much
Sir, you are just fastening up, sir. Can you please slowly tell down these 2 points, the percentage calculation?
for
Okay.
information conserved and information lost.
Yeah, if I'm changing from 3 dimension, I was in the starting, the data was in the form of 3 dimension. Okay, I'm changing from 3 dimension to 1 dimension for the better visualization purposes. Okay, how much information I'll be losing? Okay, the first question was this one. If I'm changing from 3 to 1 dimension, that means what? I'm preserving how much information? I'm changing from 3 dimension to 1 dimension, right? So
From
3
3 to 2
dimension.
in that case is 5, sir, not 1, sir.
What?
So how come it's 1 by 6? No, it should be 5 by 6, no?
It should be 5
3
by
to
6.
5 by 6. Yeah.
5 by 6 information that is preserved. So I'm losing 1 upon 6, right?
Yes, sir. So your question was same thing, right?
Sir,
Sir, preserving
yeah.
I wanted to know what is the question for which 1 by 6 is the answer.
How much percentage I'm losing the information?
How much you are losing? Huh?
Yeah.
Okay, this is conserved.
Sir, can you give the general formula?
Okay, so the general formula for this type of question is, so whatever the dimension has been converted, like from some bigger d dimension for the smaller d dimension is converted, right? And you have to calculate the information that is preserved. Okay, preserved.
Okay.
So what you'll be doing, you'll be adding all the lambdas. Okay, whatever the how many lambdas you are getting, like you'll be getting d lambdas, right? And you are converting from some bigger dimension to the smaller dimension, right? So here it will be here the lambdas will be smaller one. Okay, so this is this is the portion of information that has been preserved from converting from some bigger dimension to the smaller dimension. Okay, so this is the formula. Here for this example,
D dash should be the maximum eigenvalue, no, sir?
What?
The sum of D dash should be the maximum eigenvalue.
Yeah. Like for example, here I am converting from 3 to 1 dimension. So what I am writing? So D, the bigger dimension is lambda 3 plus lambda 2 plus lambda 1, right? And here is what I am converting to 1 dimension. That means what? Lambda 3, because this is the biggest one. This is what I will be conserving. So I am conserving how much? 3 upon 6. So 50% I am conserving.
Okay, sir. If we will go from 3 to 2, then we will add 3 lambda 3 plus lambda 2, right?
If I'm going from 3 to 2, correct.
So that will be 5 by 6. 5 by 6 of information I have conserved.
Correct. So I guess this is clear, right?
Yep.
Yes.
And information lost would be then 1 by 6, right?
Information lost is 1 minus this one, whatever the information that is conserved.
Okay. Thank you.
So one question. So total of the eigenvalues is projection variance?
Correct.
Okay. Just wanted to confirm.
Total is projection variance. If you have been asked to calculate, like for example, from 3 dimension, I'm just taking into consideration the principal component, the first principal component. That means what? I'm just taking into consideration the first principal component. Okay, that is the lambda corresponding to the maximum value. Okay.
Okay.
Okay, sir. We understood, sir.
Okay.
Let's
I
proceed,
guess
sir.
this is clear.
Sir,
The
it's
other
generally
question is
just calculate the projected variance. If they ask, then we have to calculate all the lambdas, sum up of all the lambdas.
yeah, correct.
And if you specify any principal component, then we have to add up like according to that.
Correct, correct. So
Okay,
here
sir.
I told you, right? If you have been asked to how much information is conserved from 3 to 1 dimension, here how much information is conserved from 3 to 1 or maybe 3 to 2 dimension. Just tell
Okay,
me.
so 4 by 3. 1 second, sir.
For 3 to 1, 4 by 3, by 4 by 3, 1. 100%.
100%
Both the cases 100%,
preserved,
right?
preserved
100%, sir.
and lost 0%.
Okay. So I guess this is clear. Now you have been asked to, okay, so what is the eigenvalues I was getting? This one. Eigenvector, tell me what is the eigenvector that I was getting? So the first one is -1, 0, 1, right?
So,
So first one is -1, 0, 1.
One question. So which is the fastest and easy way to calculate eigenvectors? Eigenvalues, sorry.
Eigenvalues, so see, for the 2 cross 2 you can directly calculate. Mostly you'll be
Right.
getting the 2 cross 2 in the exam. Okay.
3
I
cross
can't
3.
yeah, for 3 cross 3, the only approach is like you just have to write the characteristic equation and solve that. There is no other
Can you show
alternative.
for the 2 cross 2, sir? The shortcut.
The short one, like there also the characteristic equation, but that can be solved like very easily, right? That is what I said.
Yes, sir.
Or maybe you'll be getting you'll be getting what you are generally, you'll be getting the quadratic equation if you have 2 cross 2, right? For example, x square plus 2bxy.
Yeah, I
plus,
got it, sir.
so you can solve. Okay. So now we have to go through the 8th week also. We don't have much time. So I'll just going through all the examples. So you have got this, the eigenvector. Eigenvector is U1 is this one.
U2 is 0.
What is this
101.
U2 and what is the U3?
101.
101 and this is 010. This is right.
So in the steps, they are given one formula which may not be correct, like in the tutorial for calculating the
So
eigenvector.
now I'm telling you, don't go through the tutorial. So tutorial, there is one formula that is incorrect. So this is
Yes,
the
sir.
formula that is incorrect. See,
Yes, sir.
so this is the formula I told you in the live
Yes,
session
sir. This is
also.
what
This is, I
incorrect.
told you like 4 or 5 times this is the incorrect formula. Other than that, everything is correct. Again, one more mistake is there. To calculate the eigenvalues. The eigenvalue is not corrected, not mentioned
So what is
correctly.
the correct formula, sir, now?
So the correct formula I
Yes,
told
sir,
you.
we are
This is the
solving.
correct formula. I told like 4 or 5 times, man.
So let us solve is the problem. Let us solve.
Yes, sir. So let us solve this
Sir, we will
problem.
solve, sir. We will solve
Sir,
this one, sir.
this PDF you have uploaded, sir, because it's important. Sir,
Yeah, so you got this right. You got
Yes, and now
eigenvectors.
this
Sir, I just wanted to know where to access this PDF. That's all, sir.
I'll
From the
upload
live
it. I'll
session section.
upload this after the session for sure, and then I'll mention on the discourse. Please check it on the discourse after the lecture.
Sir, what about yesterday's session? Discourse is like a notion. We're not able to get our way through it, sir. So, like it will be under live.
Okay, you can just mail me. I'll just forward everyone.
Sir, it is
Mail.
quite difficult.
Okay, what's your mail ID? Like, we don't have your mail ID also.
Vishal@study.it.
One sec, sir. One sec. I'll make a note of it.
So let us go do it, sir.
VISHAL, Vishal.
Vishal at study.iatm.ac.in.
Okay, it's just VISHAL. That's all.
Yeah. So we have got the eigenvector, right? You have got the eigenvector. Now
Yes, sir.
tell me the formula for the projected data points. Tell me the formula for the projected data points now.
The sum of j
Sir,
equals to
actually
1
now
to
the vectors are orthogonal, sir. So can we skip the second one, sir?
Yeah, this is what I was telling in the starting. Here you will be getting the vector will be orthogonal. That is fine, not the orthogonal. So you have to check what the two conditions. The first condition is what? The mean should be 0. So this condition is not satisfied, right?
Yes, sir.
Because you have mean as 1, 1, 1. Right?
Okay, understood, sir. Yes, sir.
Second condition is what? Your mean and the other vector should be
U2 should be perpendicular to mean.
Perpendicular to mean. Here is this, that second condition is getting satisfied or not?
No.
No, sir.
Oh no, sir.
Okay, so you have to use all the other, you have to take care of everything.
Yes, sir.
Okay,
We
the
will solve.
first term, second term, every aspect you have to take care of that.
So we
So what
can
is the
just
formula that I was telling? Just tell me the formula now.
so sum of I equals to 1 to n
Summation.
and
Sum is equal to
j equals to 1 to n
1 to n
uh, xi uj
xi
uj
Xi transpose, sir.
xi transpose uj, because you are just taking the projection of all the data on ui and then uj, right?
uj
Plus
plus
Plus j
j
equals
plus
to 1 plus
n
1
plus
to
1
all the data. Okay, here
and
x bar
x bar
x bar ka transpose, because you are taking the projection of all the datas on u j and
remaining
here the
vectors u2 u3
uj,
uj
right?
yes sir.
Plus, see, why I'm writing plus here, because you'll be taking into consider here, you can just, okay,
3.
so I'll just elaborate the formula. So this is the formula that you are writing. Now what should
What
I
is
have a
basically
question. I'm sorry for interrupting.
yeah,
These U1, U2, U3, do we have to make their norm 1?
yes.
Yes.
yeah, you
Projection.
have to make that.
So in this case, they're not 1, are they?
There, no,
No
it's
sir,
not
1 by
they are
1.
3.
not 1 by
You
root
need
2
to
we
make
need to
that. The norm should be, I guess, you have to make that. Okay. So here it should be what? 1 upon root 2, you can multiply it. And here also 1 upon root 2, and here it is 1. Okay. Okay. So the formula would be what? x1 ka transpose u1 into u1, right?
yes,
Here
sir.
it should be what? This is x bar. This will be always be same. X bar into u2 plus x bar into u3. Is this clear to everyone now?
X bar is mean over here.
Here x bar is mean, u2 is the vector, the second what you can say, the eigenvector corresponding to the second eigenvalues. Okay, and the u3 is the eigenvector corresponding to the third eigenvalue. Okay, is this clear now, or do you have any doubt now?
Yes, it is.
Sir, first one is x1 bar x1 transpose. The second one is
See, what I am doing is the projection is what you are projecting the data onto the principal component first. So you are projecting all your data xi on the principal component, and you are doing what? You are projecting your mean vector, mean value, mean data point onto the other eigenvector. So what you are
okay,
doing,
sir.
the first step, you are projecting all the data on the principal component, and apart from the principal component, you are doing the projection of the mean vector onto the other eigenvectors. This is what
Okay,
we are
sir.
doing. This is the basic formula that you should be using in the exam. Everywhere you should be using.
Okay,
In
okay,
the
sir.
exam, if you are getting the problem, most probably 99% you have the chance that the x bar will be 0, or the vector will be perpendicular. The mean vector and the other, what you can say, the other eigenvectors would be perpendicular. So this is what I was telling you. Reconstruction error formula you already know. Maybe there are there also you can directly calculate 1 upon n, and then that formula you can use to calculate the reconstruction error.
Sir, so that graded assignment question number 5 is wrong according to this, right, sir?
Yeah, so it's wrong, but if you have mentioned the answer according to like if you have just considered the first term also, and then you are getting the answer, I guess that is the answer that has been given there, right?
Yes, sir. Yes.
So it will be x dash 1, na?
Where x dash one, no, see, mean will be always same, right, for all the cases.
No, after solving this,
Okay, after solving this, you'll be getting the same data point, I guess. This only.
so sir, this will be
Sir, actually, my doubt is in the first term, x1 is the data point of the first set, and
Huh.
the remaining terms mean only. We have to transpose the mean.
Yeah, this is mean. This is mean only.
Okay, okay, sir.
I guess this is clear. If you have any doubt further,
Yeah.
if you have any doubt, you can just mail me or message me, whatever you want to. You
Sir,
can do.
if in
Sir,
the
are
question,
we?
if in the question says that you need to consider only the first value, or the greatest value, then also this formula I need to put.
Yeah. That is what I am telling you. This is corresponding to the principal component. This vector, the first u1 is the principal component, and the other are the other vectors. So this is what I am telling, the projection data point, and this is the last I'm telling you. Okay, so I already told you, like, I don't know how many times.
No, so
The
sir,
last time the projects.
if I project in the three terms are there, if I project in the two dimension, should I add 2 times?
What should I add 2 times?
So here I am projecting on the biggest value. Now if I say somebody says that project in the first biggest value and second biggest
Then
value.
you should be adding this. This should, the first term should be twice, and then the last term should be. So this is what I'm telling. I equals to 1 to n means what? 1 to 1. If you are doing for 1 to 2, okay, this is fine. And then here it should be 3 to 3 only.
Okay.
So this will be x dash 1, right, sir? And then again we have to do for x2.
What x2?
X dash is the mean, right?
Man, x dash is always same. That is mean.
No. From this formula, what we will get that.
Only one vector we will get corresponding to the word.
This is x1 dash, yeah, projected value of
This will
x1.
be, you will be getting corresponding to x1, then x2, then x3.
That only I am asking, sir. Then again we have to repeat for x2, right?
Then x1, x2, because you are taking the projection, right? So you'll be projecting all each of the data point.
There's a sigma above. Just look at sigma. You have to do the summation.
I guess now it is clear to everyone, or you have any doubt? If you are able to solve this 5-6 problem that I have told you, I think so you'll be able to solve in the exam also. So
sir, can you write a formula for x2?
Same, man, x2, just write x2 here, x2 here.
And other will be same, right?
Everything will be same.
Okay.
I'm sorry, I still have some confusion. Here we say it's sigma xi transpose ui into ui, right? The first term. So here we are multiplying each data point, actual data point, with each principal component, right? So here we will do x1 into u1, x1 transpose into u1, and then bracket u1, right? And then we'll do x1 transpose into u2, because it's sigma. Yeah, it's saying
this is x bar. This is mean.
No, I'm not talking about the second term. I'm just talking about the first term. It's saying sigma xi transpose ui and then multiplied by xi, the first term. So there's a sigma over here. So what are we summing up here?
x2, u2, u2, x3, u3, u3. It will go like that.
Okay, this term you're asking.
Yes, the sigma here. What does it represent?
See, this is, so I told you, if the summation is from I equals to 1 to n, n means what? How many principal component you are considering?
N is the number of principal components, not the number of data points.
No, see, if you are converting from some 1000 dimension to some 5 dimension, so we'll be taking into consideration 5 principal component, right?
Okay. Could you just give me a clarity? N is representing the number of actual dimensions.
Okay. See, where is the
because see, I'm also doing MLT and the notations are different, so I'm getting completely confused right now. Here, what is N or M, and what is, you in your formula just now you had written N and M. So what is N and what is M?
1 second, I'll just open the search slide itself. So I'm pretty sure that M here is
N
the
is
number
the
of principal component.
Yeah, N is the number of data points and M is the dimension to which we are reducing.
M is the dimension from bigger dimension to a smaller dimension that you are going to.
Okay, so N is number of data points and M is the number of principal components that we are going to be taking.
Exactly. Correct.
Okay. So we are going from the first data point and we're looking at its product, its projection on the first weight vector uj, that's u1, then u2. So we will have gotten the sum of all the x's projections on each of these principal components by this sigma, right?
Correct.
Okay. And at the same time, then we are looking at x bar transpose with each of these principal components.
These are
So
the
this
these are not the
term will be
these are not the principal component. These are the other vectors apart from the principal component. See, I'll just clarify your doubt. I'll just open the lectures. 1 second. I'll just open the lectures.
Sir, I just want to clarify something. The principal component is the lambda value, right? Or is it the corresponding vector?
corresponding vector.
Corresponding to vector, like according to the maximum lambda.
Yeah. So the corresponding the eigenvector is the principal component. Yeah.
Correct.
Okay, sir. Thank you.
See here what we are doing. So this is the formula that sir is using. So m. Okay. So m here is the principal component, okay, that we are taking into consideration. That's why we are doing from m plus 1 to d dimension. So whatever the remaining data eigenvectors are there, that is what we are taking into consideration in the second part.
Okay.
Is it clear now? Right? So from
Okay.
m plus 1
So
to d
the
dimension.
second term will always be the same for whether we are finding the projection of x1, x2,
Correct.
x3, right? This will remain the same.
Because we are just doing the projection of the mean vector onto the other eigenvector apart from the principal component.
Yes. So this we can just calculate once and for all and then take it for
Correct,
projection
correct.
of each of these. Yeah?
Fine. Yeah.
That is only in practice, but in exam situation, most likely we won't have the second term.
Yeah, most likely I'm telling you 99% this won't, you will not be using, but like I can't guarantee you, but mostly it will be like similar. Like you'll be getting the mean as 0 mostly, or the vector
The mean
will
to
be
being orthogonal to the
orthogonal.
eigenvectors.
Yeah, the mean will be orthogonal to the remaining
Yeah,
vector.
in which case one of these terms will become 0 anyhow.
Correct.
Okay, thank you.
Okay, so
Sir, we will be doing week 8 also because
Sir, one question on
we have
this.
passed time.
Yeah, go ahead.
So what have we got now? So we have got just one.
I can't hear you.
Oh, I mean, do minus of this vector to other vectors and then square it.
I did not get you. Can you repeat that? Your voice was breaking in between.
So my question is like, now we have got 3 to 1. From 3 vectors, we have got 1 vector.
No, 3 dimension to 1 dimension, not 3 to 1.
Okay. And if you want to find the error in this case, so what should be the error?
Error you can calculate, right? There is a formula to calculate the error. Where is that? This is the error formula. Where is that? I don't know. I've written somewhere. So that reconstruction error formula is this one. The projected data. So how then you calculate the projected error? So the projected data minus the data that was given, subtract it, square it, and then divide. Do the summation for all the 3, like x1, x2, x3, and divide it by 3 to get the reconstruction error. And
So
this
first
right?
vector minus the vector we have got, then second vector minus the vector that we have got after applying PCA. So this is what we have to do. I mean, xi would be same for 3 vectors.
Okay, can you repeat that? What?
I mean,
See,
xi in this
you'll be getting this. This is given, right? This is given.
Right.
X1, x2, x3 is given. You'll be getting something. X1 bar, not bar, x1 trans, something like that. X2 and x3 after projection, right? You'll be getting some values, correct? So you'll be doing what? Whatever the value you're getting, x1 minus x square plus x2 minus x2 square plus similarly, and then divided by 3. You'll be getting the reconstruction. Okay.
But in the question over here, we have done 3 to 1 example. So we have just 1 vector.
3 to what? 3 to 1 example?
See over here. Can you go a bit down?
Okay.
Over here. So we will be getting one vector only, right? By applying this equation x1 transpose u1 u2 plus x bar transpose u2 u2. So we'll be getting just one vector, right? This is the vector we have received after applying PCA.
This is the projected point for only the first x1. Likewise,
This
we'll have
you
to
are
find for
getting
x2 and x3.
confused.
Yeah. So
See, you will be getting what after project. So see, you are projecting something. So if you are projecting something, some data is pointing somewhere, so you'll be getting in the form of 3 dimension itself. So for example, earlier the values was what? This was the value. But for example, you are getting the after projection, you are getting something like that. 101 and x2 as something 111 and then x3 something like that. Okay, so this is the projected data point. Fine.
okay. Okay.
And then you can subtract it and then get the reconstruction.
Sir, PCA is supposed to reduce the dimensions, right, sir?
Yeah.
So basically, x1 bar should be.
Again, you are getting confused. See, if you let's for example, you have x equals to y dimension. Sorry, x and it's a coordinate, and y equals to x. You have to project the data. You have to do the projection of this point. Okay, on the y equals to x. That's okay. So this will get projected on this one in term of what 2 dimension itself. But what we are doing, I'm transferring from 2 dimension to the 1 dimension on y equals to x, right? So you are getting the value point in the form of 2 dimension. But what exactly I'm doing? I'm transferring from 2 dimension to the 1 dimension itself. Is it correct or not?
But when we are projecting, we'll lose one dimension, right? We'll lose the height.
But here also see, it's a basic example, x equals to y. X equals to y is what I'm just, whatever the data point I have, I'm just converting from this x 2 dimension to the 1 dimension. This is in this straight line itself. Okay.
Yes, sir, yes.
If I'm transferring from all the points on this line, that should represent what? That will be in the form of 2 dimension. But it's what basically it is transformed from 2 dimension to 1 dimension, right?
Oh, okay, sir. Okay.
Got it, right?
Okay. Okay, thank you.
Okay, so I think so 7th week is done. If you have any further doubt, you can just ask me by mail. Maybe you have like 1 more days to revise. I'll just reply there.
I have just one general doubt that about the tomorrow session. That professor is going to take the session. Then how the session will go? If we are able to clear our doubts also in that session.
Yeah, you will be able to ask your doubt like not from week 8 because he has not taken week 8. You can take your doubt, write your doubt, like you can just read it. Whatever the doubt you have, you can just ask him in tomorrow's session. That will be 5, 6, 7th week. You can just ask him there. Okay.
Tomorrow it is from 2 p.m. Right?
Yeah, this is 2 to 4. So now week 8, I guess. Ram, are you there?
Sir, I have one request. Sir, instead of clearing this in live session where most of people are working, so sometimes they skip the live sessions. So can you please maybe make a PDF or a note or something and put it in the portal itself like an errata, so that it will make your life also easier, I guess. Because
yes,
there might
also ma'am was telling that there is some notes given for week 5 or 6 in the Discord, but I didn't found it there.
Okay, so what you're asking, should I upload all the things?
One link was shared yesterday. One shared drive link was shared yesterday.
Okay, so I'll upload it. Everything's there itself. Is that fine?
Sir, will you upload the recording also? I missed the beginning of this lecture, sir.
Yeah. What?
Yeah.
What?
Will you share the recording of this live session?
Yeah, it will be shared tomorrow. After this session will get ended, we'll share that. Okay?
Sir, we are going to do week 8 also.
Yeah, we'll do week 8 from now. So Ram will take that. Ram, are you there?
Yes, we shall. I'm there. You can stop sharing.
Okay, I'll just stop it. So from here, I guess, so week 8 will be And whatever the doubt you have from like week 6 and 7, you can ask tomorrow also. The professor Prasan will be taking the session, or maybe you can ask me. Okay, I'll just stop it.
So, sir, please share the PDF, sir, because video upload is like it will be for a long time, and instead of switching along the timestamp, we can actually see the PDF, which will be much cheaper.
Yeah, I'll upload everything after this session for sure. Okay, I can guarantee. Okay.
Yeah, most important, the PDF also. Thank you. Thank you.
Okay.
So can you share yesterday's slides?
Yeah, the slides will be shared. Okay.
Yesterday's session, sir.
Yeah, the yesterday's session's slides too will be shared. Okay.
Okay, sir.
Okay. So we look at week 8 content. So in the week 8, the main problem which others can you guys please mute it? Others please mute yourself.
Chaitanya, can you mute?
Okay. So when we have this, the main problem which we are dealing in week 8 is this optimization. Okay, solving for the optimization. When we mean by optimization is we either want to maximize the reward and then like minimize the loss, right? So suppose if a problem was given for you, like there is a cube. Okay, this is a 2D one, but imagine that this is a cube, okay, and in that cube we were asked to insert a cube. Okay, so what is the maximum volume of the cube that can be inserted in a sphere? Okay, so that could be one question. So here we want to maximize this area. Okay, so basically we will have this. We either want to maximize something, or we want to minimize something. So in this particular problem of curve problem, okay, what we have here is that we have a curve at this point. Okay, so here we have the grass. So this grass portion is fixed, obviously. It's 40, 40, and then this curve's portion, so that can vary because the curve can move. So if this point is x, y, we want this x, y or the curve to be as close to the grass as possible. So we want to minimize the distance between the x, y and then 40, 40. What's going to be the distance square? So it's going to be x1 minus 40 whole square plus x2 minus 40 whole square. We want to minimize this. Okay. So in general, for any optimization problem, okay, there is going to be an objective function which you want to minimize or maximize it. Okay, along a variable or a parameter we have. In this curve problem, the variable which we have is this x, y, that is this curve's position. Okay, and then there could be this constraints also. Okay, the inequality constraints or the equality constraints. So like this variable or parameter, right? This variable or parameter, it has to satisfy these conditions or constraints. Okay, so these are called the constraints, and in the constraints we have inequality constraints and the equality constraints. Okay, and if a particular objective problem, right, optimization problem, if it does not have any constraints, then that is called unconstrained optimization problem. Okay, so here too we have here, like in general, when you're trying to solve for optimization problem, the way you do that is the analytical way will be you find this gradient or the derivative. Okay, in this particular case you do the f dash of x equals 0, and then like you find the cases where that satisfies. Okay, so here for this particular problem of x minus 5 whole square, we want to minimize it. We know that obviously the minimum can happen at x equals to 5. Even if you differentiate it, it gives you the same answer. Okay, at x equals to 5, the minimum value occurs, and then the minimum value is 0. Okay, at 5, if we substitute this value, the f of 5 will be equal to 0. So in general, when we look at this unconstrained problem, okay, we look at the unconstrained problem. Like mostly in this week, we'll completely be looking at the unconstrained problem. Okay, in the unconstrained problem, okay. So instead of doing the analytical way, okay, if you go by the iterative way, right? If you go by the iterative way, because sometimes finding the solution analytically, it's not going to be possible when the equation is like very large. So in that particular case, what we do is we start the iterative process. In the iterative process, we start the particular point, and from that particular point we'll move towards solution. So what I mean by towards solution is, we start from somewhere around 2 here. Okay, obviously for this x minus 5 whole square, we know that the minimum occurs at 5. So we try to move towards the direction of solution. Okay, suppose if you are arbitrary, that is a starting point which you have chosen. If it is at 8, okay, you want to move towards the left side. Suppose if you're starting from 2 or after some iterative steps, you are at 2, okay, then you want to move to the right side. So sometimes this xt plus this xt plus 1 is what that means is nothing but from this particular xt point. Let's say like after some t iterations you are at xt. Okay, from this xt you want to move to the next one. Okay, so our assumption is that this next point xt plus 1, it should be close to the solution. Okay, we want to move in the direction, right? So for you to move towards xt plus 1, there's going to be this direction or the value we need to add, right, to move to that xt plus 1. Okay, this d value, as I told you, if it is 2, right, we want to move to the right, and then if it is 8, we want to move to the left. So how can you say that how to choose this d value? Okay, so if you choose this minus f dash f x, then it's going to be exactly this. Then in this particular case of 2, right? So this minus f dash f x, it will give positive, so that you can move to the right. And then when it is 8, the minus f dash f x will give you negative value, so that you will move towards left. So for irrespective of what the x value is, this minus f dash f x, it will give you the correct direction to move. Okay, so this minus f dash f x, it will give you the good direction. So why exactly minus f dash f x, we'll be discussing that in a bit. Okay, so the next problem is, okay, now we know that the good direction to move is minus f dash f x. We try to solve for this particular problem alone, this x minus 5 whole square. Okay, you start with 0. Okay, you start with 0 or 10. Okay, you start with 0. What happens is this t value which you get, it's going to give you 10. Okay, so it's going to give you 10. So and then you'll be ending up here. So since this xt plus 1 equals to xt plus d, okay, so this d minus f dash f x, it's going to be 10, and then this xt value, it's going to be 0, so you'll end up at 10. Okay, so this is still in the good direction because we want to move to the right side from 0, because the 5 the actual solution, it is in the right side, so we are moving in the right side direction. Okay, and then from 10 if you compute the same d value, you get d as minus 10. Okay, so you'll arrive at 0. So from 0 you arrive at 10, and then from 10 you'll arrive at 0. So if you just continue this, you'll just be like oscillating in between 0 and 10. You'll never be actually reaching 5. Okay, even though you're moving in the correct direction, it's just like you'll just be passing through solution, but you'll never arrive at solution. So the other important thing to keep in mind is that not just the direction is important, but then the amount with which you're moving. That is that minus f dash f x to that minus f dash f x. It's not just going to be minus f dash f x. You just need to reduce it, or you need to do something to ensure that you'll arrive at solution. Okay. So for that, what we do is we introduce this. We introduce this step size. Okay, so the step size value, we obviously do not want it to be more than 1. Okay, we want it to be lesser. Okay, so we cannot be choosing any arbitrary step value, and like we cannot be having it same. Okay, even though we can, but it may not actually be leading to solution. Okay, that is like you'll just be oscillating. You may not actually reach solution. So for you to choose a particular step size. Okay. First example here given was this 1 by 2 power t. Here the problem with this is previously we are oscillating. That's like we are never reaching it. We are just like oscillating between 0 and 10. But if you choose this 1 by 2 power t, because the step size will reduce like too much after each iterations. Okay, you may never be able to reach this 5 even after so many iterations. Okay, even after infinite iterations, you may not be able to reach the actual solution. Like we'll just be stuck at somewhere around 4. Okay, we'll just be stuck somewhere around 4. Okay, even after infinite iterations. Okay, we'll just be coming close to 4, but you'll never reach 5. So we do not want to reduce our step size too much. Okay, so then what we do is, if we choose this 1 by t plus 1, okay, 1 by t plus 1, this 1 by 2 plus 1, it's going to be a good step size, because the sum of the steps, that is just 1 by t plus 1, t equals 0 to infinity. If you do the sum of the steps, it's going to give you infinity. Previously, the sum of the steps, that is this 1 plus half plus 1 by 4 and so on, it's not going to give you infinity, it's just going to give you 2. Okay, this a by 1 minus r formula, it's going to give you 2. So since this sum of the steps is infinite, this is a good step size, because after each iteration the step size is reducing. Okay, it's reducing, but we are not reducing it too much. Okay, so this, if we choose this as like xt plus 1 is equals to xt, okay, minus eta, in place of eta, if we take it as 1 by t plus 1, okay, multiplied by this dash of x. So we have this minus f dash of x, so I have written it like this. Okay, so this, if you use this particular formula, that is, if you choose the step size as 1 by t plus 1, okay, then that particular algorithm is called as gradient descent algorithm. If you choose the step size as 1 by t plus 1, okay, then that particular algorithm, it's called as this gradient descent algorithm. Okay, until now, any questions here? You guys are following me, right?
Do we solve any sums, sir?
What? Can we look at the sums you're asking? Some problem?
Yes, sir. Yeah.
We'll definitely look at it. We'll look at it at the end. Okay.
Okay, sir. Okay.
Yeah. So, and then the next one would be, okay, we are arriving at a solution, okay, but then are we arriving at the global minima? Okay, so what happens is our formula is xt plus 1 is equals to xt minus eta f dash of x. Okay, when will our problem end? That is when this f dash of xt, when this f dash of xt is 0, you will stop. Okay, your algorithm stops. It will not move further. Okay, so basically you'll be stopping at the point where f dash of x is 0. Okay, but then if you look at this graph here, at this particular point, the f dash of x will be 0. This particular point, f dash of x will be 0. Even here. Okay, even somewhere around here also we have f dash of x is 0. So depending upon your starting point, that is if you choose this as a starting point, we'll end up at here after some n iterations. Okay, after some finite number of iterations, we'll end up at here. But then if you choose here, we'll end up at here. Okay, at this particular minimum point. So depending upon your starting point, your algorithm, it will stop at some particular value. Okay, and the problem here is, for this particular graph, this is a local minima, but this is not a global minima. Okay, this is a local minima. When I mean by local minima, what I mean is within the small x value, this is going to be a minima that's going to be possible. But the global minima, that is for the entire function, this is the global minima. Okay, this is the global minima. So our gradient descent algorithm, it will not be useful for this particular kind of functions. Okay, so the functions which you want is the functions for which the this gradient descent algorithm applies very well is for a particular function that has this local minima is same as a global minima. Okay, every local minima should be same as a global minima. Then those particular functions are called Convex functions. And for those functions, this will work well. Okay, for those particular functions, this gradient descent algorithm works well. All right, clear?
Yes, sir.
So did you say convex functions?
What?
I didn't hear that properly.
Yeah.
No, I didn't hear that properly. Did you say convex functions?
Okay, so the convex functions, for the convex functions, we have this local minima as the same as a global minima. Okay, so if you have your local minima to be same as this global minima, then those kind of functions are called as convex functions. Okay, and for the convex functions, your gradient descent algorithm works well. That is, doesn't matter at which point you start. you'll always end up at a local minima, and since the local minima is also a global minima, you'll be minimizing your objective function. Okay, but let's say if your local minima is not always a global minima, then whatever minimum value you got, that's not the actual minimum value of the entire function. Okay, that is as you can see here. Suppose let's say I use my gradient descent algorithm. Okay, I took this as a starting point, and then I end up at here. Okay, this is a local minima, but this is not a global minima. Okay, so even though my gradient descent algorithm gave me some answer, but that's not the actual answer. Okay, we want. So, but for this convex functions, our gradient descent algorithm gives you the correct answer, irrespective of your starting point. Okay.
So sir, for convex function, only one minima should be there, right?
Yeah. Like
only one local minima. Also.
One local minima value will be there. The points at which the local minima happens, that can be many. Okay.
Oh, okay, sir.
So why exactly we are choosing this minus f dash of x, we'll be explaining now. So if you look at this Taylor series expansion, f of x plus eta d, it's going to give you f of x. Yeah.
Question. Although this is pertaining to week 9, it is related to what you just
What?
said, that convex functions would have every local minima being a global minima.
Right.
So there was this activity 9.6 question 5 where we were supposed to choose the true statements about convex function, and one of the true statements as per the answer was that there may be multiple local minima.
Yeah.
Like
Yeah.
if you look at the quadratic function that you have chosen, Sir has chosen over here, there is only one local minimum, which will obviously be a global minimum. How can there be multiple local minima, and how can each of these local minima can be global minima?
There can be multiple local minima. Hey, there can be multiple local minima. Okay, can be. It's not should be.
That means each of these local minima then will be global minima.
Yeah. That's what we are talking about, right? Each and every local minima will be a global minima.
Sort of like the sine function.
Sine function is not a convex function, but for them, yeah. For them, each and every local minima, that's going to be a global minima there. But it's not exactly the convex function. Okay? It's like bit more than that. Like for the convex functions, we have this entire local minima to this global minima. But the sine function, it's not.
It's not a convex function.
It's not a
Sorry. So that is why I'm not able to visualize how can there be multiple local minima and yet each of them is a global minima. There will be a lot of turns in this function.
Okay, let's say like you have this. Here you have all these points. All these points have the local minima, right?
Yes.
Local minima same as a global minima, right?
Yeah, thank
Okay.
you so much. This example really clarified.
Yeah. Okay, clear?
Yes, perfect.
So we have here for Taylor series, the beauty about this Taylor series is that when you have any function f of x plus eta d, okay, if you want to get the function value at any point, and then if you know all the evaluations, by evaluation what I mean is at some particular point x, okay, if you know the entire data, that is if you know f of x, f dash f x, f double dash f x, and f triple dash f x, you can get the function value at any point. Okay, that's what this Taylor series gives. Okay, it gives you global information. If you have the entire local information, okay? You should have the entire local information. That's what is important. Okay. Now if this eta d is small, okay, this is this Taylor series expansion one. Okay, now if this eta d is small, then we can ignore this eta square d square because that's going to be even smaller. And then the later one, eta cube d cube by 3 factorial, those two we can ignore. Okay, f triple dash f x and all that we can ignore. So when you ignore all the higher terms, what you're left with is f of x plus eta d is equals to f of x plus eta d f dash f x. Okay, so suppose let's say this is our xt plus 1. Okay, this is our xt plus 1 and then this is our xt. We want to minimize our function, right? We want to minimize f of x. Okay, when you want to minimize f of x, So the direction in which you want to move, that is this xt plus 1, we want this f of xt plus 1 to be less than f of x. So basically we want this f of x plus eta d to be less than f of x. Or in other words, f of x plus eta d minus f of x should always be less than or equal to 0. Okay. So since this f of x plus eta d minus f of x, it is equals to eta d f dash f x, we want this eta d f dash f x to be always less than or equal to 0. Okay. I'm saying this less than or equal to 0 because it can happen that f dash f x equals 0 can happen, right? At the local minimum or the global minimum, it can happen. So that's why I said less than or equal to 0, even though it's written here less than 0. Okay. So we want it always to be like less than or equal to 0. For this eta d f dash f x to be less than 0, this eta anyway is positive. Okay. So this d f dash f x to be should always be less than or equal to 0, and that's the reason we choose this d as minus f dash f x. So when you have this d as minus f dash f x, this overall value is going to be eta minus f dash f x whole square. So this anyway is going to be positive. This is positive, and then this, if we include this minus sign, it's going to be the entire value. It's always going to be less than or equal to 0, always. Clear? And that's the reason we chooses d as minus f dash f x. Okay? Clear? Okay, 4. Later on, until now what we have seen is we have looked at the functions which has a single parameter. Okay? We can be having this higher dimensions too. Okay, where we have like multiple variables x1, x2, x3, and so on. We can be having many. So there we cannot be using the derivative. So here we will be using this gradient, okay, where the update rule will be like previously what we had is we have this xt plus 1 equals to xt minus eta f dash f x, right? So instead of the f dash f x, we will be using gradient here, gradient f. Okay. So this gradient is nothing but the partial derivative with respect to each of the variables. So dou f by dou x1, dou f by dou x2, because we have here the variables are x1, x2. If you have multiple variables there, it will be doing further. Dou f by dou x3, dou f by dou x4, and so on. Okay, when you have multiple variables, you'll be just doing all that. And then previously xt is just a single variable, right? But now this xt, it's going to be a vector. So it's going to be like xt plus 1 is going to be a vector. It's going to be xt will be a vector again minus eta gradient f. So as we can see here, gradient f is a vector. So it's going to be something like this particular example, it's going to be ab minus eta dou f by dou x1 at a comma b, dou f by dou x2 at a comma b. Okay, this is going to give you some particular vector, like let's say if this is this, let's call like a1, okay, a1 b1. Okay, from this a1 b1 you can get a2 b2 and so on. All right, is this clear? How you do the gradient descent algorithm for higher orders, higher dimensions? Okay. You can expect a problem from the gradient descent. You can expect a problem for gradient descent, and it's going to be the step size will be mentioned to you. The step size eta will be mentioned to you, and then like you can just follow that to get your solution. Okay, whatever is asked of. Clear? Hello.
Yes. Yes, sir.
Okay. So this we have already discussed this why exactly the d2 minus f dash f x and the higher dimension is also discussed. This is just an example. Okay.
Sir,
so,
can we expect the questions like what you told in the earlier, like inside a circle, inside the ellipse, a rectangle is inscribed?
Yeah. Those
any constraint.
Yeah. You can expect that. So
those ones are a little tough.
So yeah, it might appear like a little tough, but see, you could whatever the problem is going to be, right? So when they ask you for the analytical one, the gradient descent, it's going to be easy. But those kinds of problems, it could be a little tricky. But what you need to notice is there's going to be some objective for every minimization or maximization problem. There's going to be an objective. Okay.
Yes, sir.
This particular problem of cube in a sphere. Okay. So the objective is maximizing a cube volume, right? What is going to be cube volume? Cube volume is x cube, right?
Yes, sir.
Right? Clear? And then what is the constraint here? The constraint here is that it should be present within the sphere, right? So this is going to be R, correct?
Okay.
So this is going to be R, okay. Like the maximum value it can take it is this R only. Okay, it cannot be going more than that. So by looking at this R value, you can directly be getting this. Okay, you can directly get this. All right.
Okay, sir.
So you can directly be getting this, and then so this is going to be what? This is a square, right? This is a square, and then this is going to be 2R is going to be equals to root 2. Like if you take this side as this x, right? Okay, yeah. 2R is going to be root 2 into x, which is going to give you x as root 2R. Okay, and then the maximum volume of the cube will be something like 2 root 2 R cube. Okay. Clear?
Okay. Okay, sir.
So like in even though it could be like multiple dimensions or whatever, so the main thing you need to notice is there is going to be an objective. There is going to be an objective. Okay, and then there is going to be some constraints. Okay, by using the constraints, you want to reduce we want to reduce the objective function to a single variable. Okay, we want to reduce the objective value to objective function to be a single variable. To minimize it or maximize it, generally we do the differentiation. In this particular case, the differentiation is not required because it's like straightforward. But in some cases, the differentiation might be like required. Okay. Clear?
Okay, sir. Do we solve any problems related to this, sir, today?
Yeah, we can solve.
Okay, sir.
Sir, I have just one thing to say. In graded assignment 8, in question 3, we were supposed to find the volume of the largest cone that could be inscribed in a circle. So I did it, and I solved it, but I took pi as 3.14 instead of 22/7. So my figure came to 267.95, and it did not fall within the answer range, so I got it wrong.
Okay, so what was the range that was given there in the answer?
It was given as 268 to 269. There was no specification on how many decimal points to give. I did it at 267.95, which I could have rounded off to 268, but I didn't round off. And the range was from 268 to 269.
I mean, you could have used the pi value on the calculator.
I didn't think that I mean, if I use 3.14, it would give me a wrong answer. I used 3.14.
Yeah, I understand what is it. Okay, so generally in the quiz exam, okay, we take care of that. Even if you take even if you're taking 22/7, ideally you should have been given marks. Okay, but make sure that assuming pi to be 22/7 is okay, but don't round off other values.
No, I did not round off a single value. The only thing was I took pi as 3.14.
Okay, then
I didn't round off anything. I just took the pi as 3.14, and then I didn't even round off the final answer. Had I rounded off the final answer, I would have fallen within the range because it was 267.95 and the range started from 268. But I got it wrong just because I didn't round off. And well, my mistake was I took pi as 3.14. So should I be very, very careful about using pi only and only as 22/7?
No. Actually, in the quiz exam, we ensure that we already mentioned that it should be like 2 decimal accuracy and so on. Okay, 2 decimal accuracy or 1 decimal accuracy, and rest assured, like if you face the same problem in the quiz, right, you can always raise that issue in the discourse, because the main thing which we look for is for you to get the idea right. Okay, Just because you took this 22/7, we can't be reducing your marks. So we'll definitely be giving.
I didn't take 22/7. I took 3.14.
Okay, if you're taking 3.1 for 22/7, whatever it is,
It should be the same, isn't
yeah,
it?
yeah, we should be giving you marks.
So
Okay?
should I be posting this particular issue,
Yeah, yeah,
graded
yeah.
assignment?
Right.
Where should I put it on discourse?
Yeah, yeah. So regarding this graded assignment, right now the deadline is already done, so we can't be helping you there. But in quiz, we can definitely help you. Okay.
All right, thank you.
Okay. So this gradient and all. So this Taylor series, which we have, the same one you can be having for this higher orders too. Okay. What we had here is for the single dimension one, but for the higher order, we use this transpose. Okay. Since this gradient, this gradient f of x, that's going to be a vector, and then this d is also going to be a vector. So we do this d transpose gradient f of x, which is going to give you a scalar, because this is a dot product between d and gradient f, right? So it's going to give an vector. And one thing you need to keep in mind is, because most of you might be already be aware, no matter what the input value is, that is f of x, right? This x could be a single dimension or it could be a vector, but f of x will always be a scalar. Okay, the function value will always be scalar. Okay, that part you should be looking at it, because if you look at volume is function of volume of a cone. Okay, volume of a cone is what? Volume of cone, V of cone I mentioned. It's going to be pi r square h by 3. Am I correct? Or it's something else? It's correct, right? Pi r square h by 3. Is this clear? Okay, yeah. So this volume of a cone, it's a function of r and h. But pi r square h by 3, it's going to be scalar. So the function value will always be scalar. Keep that in mind. Okay.
So, but in a cow example, fx is scalar, right?
F of x is scalar. Yeah. There too, you're measuring the distance between x1, x2. Sorry, x1, x2 point to 40, 40. You are measuring the distance between these two. So it's going to be a scalar only. So because you have x1 minus 40 whole square plus x2 minus 40 whole square, ultimately it's going to be a scalar. Okay.
Okay. Thank you, sir.
Yeah. So why exactly we are looking for this? This b as is minus f dash f x is, like, what's even more special is we'll discuss even further there. We saw there that if you take ds minus f dash f x, that minus f dash f x whole square was less than 0. But what about the case of gradient? Okay, the gradient is a vector, right? Gradient f of x is a vector, right? So when you're doing this d transpose gradient f of x, you want this d transpose gradient f of x to be less than 0. Okay. Generally, for any vector, okay, you take any vector, okay. In this particular case, it's gradient f, but let's call it like any w vector, okay. So when you're doing the dot product with another vector, let's say like d here, okay. So this d could be in this direction, this. It could be in many directions, right? Okay. So, but when will this d transpose gradient f be less than 0? One thing you need to notice is, when it is like 90 degree, we know that the dot product is 0. That is, the d transpose gradient f is 0. When they are parallel, it's going to be positive. That is, if d is going to be the same direction, then that's going to be positive. So all these yellow colored regions, if you take any vector in these yellow colored regions, okay, the dot product of this particular vector with respect to w, it's going to be greater than 0. Okay. Because the theta, the angle between the two vectors, it's less than 90 degree. So the gradient value, sorry, the dot product value will always be greater than 0. And in this green colored region, okay, the angle is greater than 90. Okay, this angle theta here, it's like greater than 90. So when you have this theta to be greater than 90, then you have d transpose gradient to be less than 0. Okay. So here too, you have like multiple directions. So we want this d transpose gradient to be gradient f of x to be less than 0, right? So we could have chosen any of this direction, but we are choosing exactly opposite to it. Okay, we are choosing d to be minus gradient f because it is like the steepest descent. Okay, it gives you the least negative value possible. Okay, that's the reason we go for D to be minus gradient f. Okay, because this angle is 180 degree, the dot product between them, it's going to be the least value possible. Okay, or the steepest. So that's the reason we call this gradient descent algorithm to be the steepest descent algorithm. Okay, clear this idea? Yes, no? Guys there? Right?
Yeah, okay, sir.
Okay. So we'll be having this like that. Okay, that is this. And when D is minus gradient f, we have this steepest descent. Okay, in all the other directions. Okay, you could be having it to be less than 0, but it won't be as least as when you choose this minus gradient f. Okay. All right. So now we look at the problems. We're done with this theory. Okay, we look at the problem. So you want me to choose some arbitrary problems, or like what do you want? How do you suggest it?
Sir, whichever is useful to quiz 2, sir. More prominently based on that.
Quiz 2.
Quiz 2 problem.
Yes, sir.
Related to quiz 2, I told you one, that is this maximization minimization problem you can try. And then I actually told you how to solve that maximization minimization problem. Like maximization or minimization, whichever one it is.
So we will try that one problem related to that, sir.
Okay, so let's say like there is a you have an ellipse, okay?
Okay, sir.
You have an ellipse, and then you want to insert a square, you want to insert a circle there. Okay?
Okay, sir.
Is this clear? So now the problem is, what's going to be the maximum, I mean, this circle, what's going to be the maximum area of circle that can be inscribed in this in this ellipse. Okay? So in the ellipse, we know that each and every point in ellipse, it should be satisfying. This is going to be center. Okay, obviously the center of the circle, it's going to be the circle, it's going to be center of ellipse too. Okay, so if you take a point in this circle, this x comma y thing, circle as well as the ellipse both. Okay, so we want this x comma y, it should be satisfying. What's going to be the equation of ellipse? X1, let's take like
by a plus
x square by a square, or x square by a plus
y by
y
b.
square by b square should be equals to 1, right?
Yes, sir.
And then the equation for circle, it's going to be something like x square plus y square is equal to something like constant square. All right? Clear?
How did we get A and B? What are A and B? The center?
No. This is going to be this A, this is going to be A, and then this is going to be B. If 0, 0 is the center of the ellipse, 0, 0 is center of the ellipse, and A is going to be this major axis and B is going to be the length of the minor axis. Okay? Clear? This one?
So x square plus y square equal to c square is the equation for ellipse, or for
This is for circle.
circle?
This is for ellipse.
Okay.
Okay.
That c squared is the radius, sir?
C square, yeah, C square is the radius of the circle.
That is r squared.
Yeah.
What are x and y?
X and y, it's like the point x comma y is the, it's like if x comma y is a point on the ellipse, then it should satisfy this condition. If x comma y is the point on circle, then it should satisfy this condition. Okay?
Okay.
Is this clear?
Sir, can I be very honest? I don't know much properties about ellipses, so I would never arrive at these formulas. Even if I know all the
you don't have to worry about whether it's called ellipse or not, but all you have to worry about is this equation.
Yeah, I would never be able to arrive at this equation
Okay.
because I don't know these
Don't worry
properties.
about it, okay? Okay, don't forget about that there is an ellipse, okay? Let's just solve this. This is a constraint and this is the equation, okay? All right.
Which
So
is the
can
constraint?
see
So
the
you will
question?
be giving this constraint, no, sir, in the question?
Yeah, yeah. For any problem, there should be a constraint, right? We'll always
Yes.
give you a constraint.
Which is the constraint, sir? The ellipse one or the circle
The
one?
ellipse is going to be a constraint.
So, but in exam we
And
will have
circle is okay. We have to maximize that. Okay.
Yeah.
we will have the equation
we
in the
have to-
exam or just a statement like we have to fix the circle in the ellipse.
Yes. We have an ellipse, and then in that we want to fit this circle.
No, sir. My question is that suppose we don't know the equation of ellipse. So what will we do then?
Yeah, like I don't know.
I have given you the equation of ellipse. Yeah, I have given you this x square by a square plus y square
In
plus b
this
square.
case, you have, but then there are so many variations to problems where I would, at least
No.
I would not know the
Like,
properties.
Okay, let's say like I'm giving you some other thing. Okay, I'm giving you this xy is equal to something like b. Okay, 100. Okay, I'm giving you this equation. Okay, based on this, I'm asking you to maximize something like x plus y.
Something that like that can be done, but something
Okay,
like the,
and you know this xy equals to 100 is called a hyperbola. You don't know, right? You need not know also. You need not have to worry about it. All you have to know is xy equals 100. 100 is a constant. From this, you'll find a solution. That's it.
But how will we arrive at that equation?
exactly.
This xy equals 100 equation I'll give you. That's what
Yeah, that's what I'm asking. You will be giving us the equation, right?
Yeah.
Even of the ellipse. Even of the ellipse.
I'll tell you that xy equals to 100 is a constraint. Maximize x plus y. That's what I'm telling.
You will also give this ellipse formula if supposing an ellipse.
Yeah. I will always give you the ellipse formula. Okay. All I'm saying is, you call this xy to be hyperbola or parabola or whatever, it doesn't matter. That's what I'm trying to say.
As long as we have the equation, it doesn't matter what we call it.
If we have that,
Yeah, I'll give you equation. That's all that matters to you.
yes, if we have the minimization or maximization statement and the constraint statement, I think we can do it.
Yeah, you're sorted.
Yes, we're sorted then. Otherwise, we're doomed.
No, we will give you. Okay, we won't expect you to be some math geniuses or something.
So can we see the questions? Actually, I missed the question. What is the
Yes,
question?
sir, it's already getting.
The question is this.
Look into the question, sir.
Yes, I'll write somewhere where there's some gap. I'll use this. Okay, so we have here ellipse. Okay, and then it's going to be circle which you want to, and then like you want to look at the maximum area of circle that can be inscribed in a ellipse. Okay, actually by looking at it itself you can tell the solution. Okay, can someone guess what's going to be the area of circle, maximum area of circle?
4 parts, sir.
Pi a square is going to be maximum area of circle. That can be inscribed. Okay, but let's solve it. Okay, so we have here x square by a square plus y square by b square is equals to 1, and then this x square plus y square is equals to c square. Okay, so this particular point
What is C here, sir? What is C?
What? C.
What is C here?
It is radius, r square.
Sir, here C is A, sir. Sir, here C is A, right?
C is A there. I know C is the A there, but you do not know that C is A, right? Let's assume that you don't know what this.
Okay.
What that is. Okay, you do not know that C can be A. Okay, assume it to be something like R. Okay, all right. Okay.
Yeah, got it, sir.
Okay, yeah. So when we have this x comma y, we know that there is going to be minus x minus y, because minus x minus y, when x comma y satisfies this, minus x minus y, it satisfies this equation as well as this equation, right? Correct? Or
Yes, sir.
correct now? Okay.
Sir, because the points are both on the circle and the
Yes. Okay. So when you take this minus x minus y, we know that if you have x comma y and then this you have this minus x minus y, we know that this is going to be diameter. All right. When you have x comma y and then minus x minus y, that's going to be the diameter, right?
Yes.
Right.
Yes,
Right?
sir.
Okay. Now we have. Okay. Now we have what's going to be the diameter d. D is going to be x minus of minus x 2x whole square. Okay, d square is going to be 2x whole square plus 2y whole square. All right.
Yes. 4x squared.
How do you get that 2x square plus?
This d is going to be this the distance between these two, right? Square root of distance between these two, right? X comma y and then this minus x minus y.
Yeah. X1
Okay.
minus x2 the whole square.
Okay, sir. Okay.
Okay, so you are going to get 4 into square root of x square plus y square. I guess. Correct?
Yes, sir.
Yeah, so basically you're not getting much there. You're getting the same equation. And then what we have there is, we have here r equals to square root of x square plus y square. D square is equals to 4 into square root of x square plus y square. So r is going to be square root of x square plus y square. And then we know that y square is equals to 1 minus x square by a square into b square. Correct? From this equation?
Yes, sir.
Okay, so we will just substitute this. Yeah. You need to get this r is as x square plus 1 minus x square by a square into b square, right? So this is going to be b square minus square minus b square into x square. Yeah, into x square by a square. Okay. So our overall point is that okay, this is going to be r. R is going to be this. Okay. Now our overall aim is to maximize this r, right? Correct? You want to maximize this r. So for that to happen, okay, it could just be that let's look at this corner cases. Okay. So a square minus b square by a square value, okay, it can either be positive or negative. That is when a is greater than b, a square minus b square is going to be negative. Correct? You guys following me?
So the step is not clear, sir.
A square minus b square, we have this equation, right? 1 minus of x square by a square into b square. This equation you have?
Yeah.
1 minus of x square by a square into b square, right? Because this is y square.
Okay.
Okay. This is y square.
Okay.
We replace this
yes,
y
sir.
square as 1 minus x square by a square into this b square.
Yes.
Okay. So now if you just readjust this, what you're getting is you're getting b square minus of a square minus b square into x square by a square. Okay. If you readjust this, you're getting this.
Okay.
All right. So here there are like two scenarios. Okay. When a is greater than b, okay, when a is greater than b, this a square minus b square is going to be positive. Correct?
Yes.
And then this a square is positive, x square will always be positive. So the maximum value of r can be equals to b.
Okay.
Okay? That's it. You got it. In our particular case, we have
I'm
here
sorry,
a.
I didn't get the last part. How we got that? If A is greater than B,
If a is greater than b, a square minus b square will always be positive.
right?
A square minus b square all multiplied by x square will always be positive.
Yes.
Divided by a square will always be positive.
Right.
We want to minimize this value, right? Because there is a minus here.
Yes.
Yes.
So the only way to minimize is if you get this x value as 0. If you take x as 0, you'll be minimizing it, and then this b square value B square values R equals to B is what you'll get. Okay.
Okay, so at most R can be equal to B because
Yeah,
the
yeah,
second
yeah.
term
That
can
is,
be at most 0,
right.
but A can never be less than B.
Yeah, yeah. So that is when A is greater than B.
Okay.
Okay. What about like A is like less than B? Okay, if A is less than B, then A square minus B square is going to be less than 0. Right?
Yeah.
So this minus of A square minus B square is going to be greater than 0. Correct?
Yeah.
Okay, so then what we want to do is we want to, if A is less than B, yeah.
So we have a doubt, sir. Okay, can you scroll up? So in terms of we're doing more like a coordinate geometry, but we need to like in terms of the maximum minima, right? So with the constraints.
Yeah, yeah, yeah.
How to do that, sir? Like
Maximum minimum the constraints you ask. How to do the constraints?
no, I just want we need to frame it up right first. After like let's say we are given this question, so we need to frame this right, the constraint and what we want to maximize.
See, the constraint is this one: x square by a square plus y square by b square equals to 1. Okay. What you want to maximize is you want to maximize the area of circle. And then any point in that circle that satisfies this equation x square plus y square equals to r square.
So actually, we want to maximize d square, right? So if
you want to maximize r there.
I mean r. If you want to maximize r, where r is the radius of this inscribed circle, and here x square minus a square, x square by a square plus y square by b square equals 1. So this is something which we want to maximize, right? This is not the constraint, na? Constraint is that you cannot have x more than or the radius more than a, right?
See, this radius r you are talking about?
Radius of the inscribed circle.
Yeah. The radius r cannot be greater than a. That's why I said that by looking at itself, we can say that the maximum area that can be pi a square. Okay.
Yeah, in this
by
case,
looking at itself, we can be telling about it.
Yes, so in this case it is quite easy. But let's say it's some other function which says about some other geometric figure for which we don't know how it is. So I just wanted to know how to formulate into the constraint, because once we formulate, we can go with our usual minimum maxima, right? That's right.
You just do the same thing. You just do the same thing. What you do is you write this constraint, okay, and then you look at like what you want to maximize, okay, and based on that you just go for it. That's it.
Yes, go for the first derivative. Equate the first derivative to 0. Take the value, same thing, right?
Yeah. Okay. X square plus y square is equal to something like r square, let's say, okay, and then I want to maximize the product of x y. Okay, so this is going to be our objective function. These are constraints. So by using constraint, I can get y square as x square minus x square. So and then I can substitute that value here. X into y is going to be square root of r square minus x square. This is my objective function. Now it is just in terms of in the function of x only now. Okay. Now by doing the derivative, I can get the point where the derivative is 0, right? That is, I'll look at this f dash of x equals 0. I'll find the point x. By using x, I'll get y.
So
by using x and
so
y,
x square plus y square equal to r square is the values that you will be working with, but objective function is x y.
No, the x square plus y square equals r square. That's going to be constraint. Want to maximize x y.
Okay. So the objective function means the one which you have maximized.
Which you are maximizing or minimizing.
Minimizing.
The
Okay.
constraint is the one which you should be satisfying. Okay.
Come again. Sorry. What is it?
The constraint is the condition which you should be satisfying.
Okay.
The objective function is like what you want to minimize or maximize.
Okay. So the replacement will go from the constraint to the objective function, right?
Yeah.
Okay.
But it should be forming this objective function correctly. Okay? And it should be coming properly from the constraint to the objective function. Okay, that is this. I have replaced this y as square root of r square minus x square. Okay, this should be done properly. Okay, if you don't do this correctly, then you might end up with the wrong answer. Okay, so this is what we have for this maximization minimization, and then the gradient descent algorithm, that's going to be straightforward. Okay, can only get the straightforward kind of questions there. And
this question is solved all the.
Yeah.
Is this question is solved? Like we get the answer for this.
Yeah, the discussion is on the kind of problems you'll get in quest.
How many will get from week 8?
What?
How many questions can we expect from week 8?
From week 8, you can get from 3 to 4. Okay, 3 to 4 questions you can expect.
And what is the answer of this question? When R is equal to B, then it will be maximized?
See, whichever one is the minimum, right? We'll take that. It can be that only. Okay, if A is minimum, then the maximum radius, it can be A square. If B is minimum, then that's going to be pi B square. Okay.
So because if I look at the graph, to B is the length. I mean, if R equal to B, that cannot be possible.
Right, here if R equals to B should happen, then it's going to be something like this. It's going to be like crossing the ellipse, so this cannot happen.
Yep.
Okay. Yeah.
So the constraint here is that like the area of circle
points of circle, it should
cannot go
ellipse.
beyond area of ellipse, right?
Right.
Okay.
Okay, so yeah, any other questions here?
Sir, what will be the weightage for this week, sir?
You can expect like somewhere around 20 to 25%. Yeah, we have like 4 weeks, right? 5, 6, 7, 8, yeah. 20 to 25% you can expect.
So paper is for 50 marks or 100 marks?
20 to 25, that's like 20 to 30% you can expect.
Okay, sir.
I have one question from practice assignment, question number 3.
Question number 3.
We need to fit cone in a circle.
You need to fit what?
Cone in a circle.
Yeah.
So can we solve this?
So that's not cone in a circle. That's going to cone in a cube. Okay, not cube, sphere. Sorry. The 3-dimensional version of circle, that's going to be sphere. It's going to be cone in a sphere, not a circle.
Okay.
Yeah. Any other questions here?
I mean, I'm looking for how can we solve that and how can we get the exact answer for this question, because I'm having some difficulties on it.
Okay, I won't be solving the entire problem, but I'll give you the way to solve it. Okay. Assume this to be a 3-dimensional figure, and this is going to be your cone. This is going to be the circle of the sphere. Okay. This is going to be R. Okay, let's call the center of the radius of the sphere to be capital R. The radius of this cone, that is the base, it's going to be smaller. Okay. This entire value, it's going to be h. Okay, height. And this is going to be equal to h minus r. And then from the center point to this point, this distance is going to be h minus r, right? And from this point to here, it is going to be capital R because this point lies in circle. Okay. I'll rewrite this here. We have here, this is h minus r. This is the center of the sphere. Okay. And this is the center of the base of the cone. Okay. This is going to be and this is going to be smaller. And this is going to be capital R. Now we know that r square plus h minus r whole square is going to be equal to r square. First by the Pythagoras theorem. Okay. Now we have, what is the volume of the cone? 1/3 pi r square h, correct? In place of r square, you rewrite this r square is equals to capital R square minus h minus capital R whole square. Okay, we just rewrite this entire value here. Yeah, multiplied by h. Now this is a function of h, right? This volume is a function of h now. You differentiate it with respect to h and then equate it to 0. You get some particular h value. By using that h value, you can get the r value. Okay. Once you know the h and r, you get the volume of cone.
Okay. Thank you.
Any other questions?
So I have one question. This question is from the last quiz. Can I can I dictate that to you?
Yeah.
Okay, just a second. So the question is that the distance of the point on the sphere x square plus y square plus z square is equals to 3 is farthest from the point 2, 2, 2, and we have to find the distance maximum.
Can you share a screen?
Yeah, sure, I can share my screen.
Yeah.
Just a second.
The question is from VK, right?
Yes, sir. Just a second.
Yeah, you can share a screen.
So is this visible, the screen?
Yes. The distance of the point on sphere x square plus y square plus z square farthest from the point yes. Okay. They can stop sharing.
Yeah.
Yeah, Ram, can I take this question?
Yeah.
Yeah, so this question can be you can solve with the help of Lagrange multiplier. Okay, so maybe with the geometry also you can solve, but the Lagrange multiplier you just have to what you already know that that the equation, right? So gradient of f function, you can choose that which one is the optimization. The optimization problem was what you need. Okay, so can you share the screen once again? I'll just
sure.
I'll dictate it here itself. I guess this is a problem from 9th week, not 8th week.
Okay, so basically this was a question in the last quiz. I was doing the paper, so
Okay,
I got confused.
Okay, so this you can do with, see, so the distance, you need to calculate the distance of the point on the, so farthest from the point, this one. Okay, so the distance farthest, you can choose the minimum and then can add the radius, right? Are you able to understand? You can calculate the minimum distance from this 2 to 2 and then add the radius of the sphere. That will be the farthest point, right?
Yeah, okay.
Correct. So the what is the optimization problem for you? So the optimization problem would be the distance xyz. Maybe that you can assume that xyz is a point on a sphere. Xyz, just take the point xyz and calculate the distance. That will be your optimization problem that you need to minimize. And then after that minimizing, you just have to do add the what you can say the radius of the circle. That will be √3. Okay.
Okay. So the equation that I'm basically not able to form the equation.
So the equation will be under root of x minus 2 ka whole square plus y minus 2 ka whole square plus z minus 2 ka whole square. Whether you are minimizing d or d square, both are same. Okay.
Okay.
So function f can work as here. The f will be what? X minus 2 ka whole square plus y minus 2 ka whole square plus z minus 2 ka whole square. That will be your optimization problem. And what is your constant? The constant is that point should lie on this pair. Okay, this will be a constant problem with the equalization concept. So there you will be using the del of f equals to lambda times del of g, where lambda can take any values, any positive or negative, doesn't matter. Okay, so you can do that partial differentiation of that f, and then the g will work there. The g will be x square plus y square plus z square equals to 3. And if you solve that, you will get the value of xyz and take the value of xyz, and then you can calculate the distance of from 2 to 2 and then add root 3 to get the farthest distance.
Okay, sir. Okay. Thank you.
Yeah, thank you. I guess we are done with today's session, right, Ram?
Yeah.
Yeah, so
can we discuss some questions from week 8?
Week 8, I guess.
Sir, don't we expect questions like this? No, sir, because this belongs to week 9, na?
No, the week 9 questions will not be there. So what
Yes,
about
sir.
the mathematical innovation?
This was from week
Okay,
8.
sir. Okay, sir.
It was from week 8, not from week 9.
Sir, if you are okay, can you please solve mock quiz the 2 questions, sir, the last 2 questions?
So we do not have the time to solve it. So maybe we like solving it tomorrow. Okay. First, what we do is
okay.
We'll be releasing the solution for that, and after that we can be looking at the solutions there. Okay, that even if we still have doubts, we can be discussing in the tomorrow session after professor is done, right? We can discuss it then. Okay.
Okay, sir. Thank you.
Okay, sir.
But
we are
once
not-
again, you can explain about important point related to question.
Important point for the quiz. I already told you in the last session also. So from week 5, you can you need to from week 5, I guess you have to. There can be some problems which are like very conceptual based type of problems. So you can go through the notes, whatever you have for the. I guess Karthik has also provided you the notes, and then you have the last yesterday's session, whatever the questions has been discussed, you can just repeat it, like you can just go through it again. 6th week, there can be a question on SVD. You already are aware of how to solve that. I guess Nikita's solved some problem regarding the SVD. And then there can be some problem from like 3 to 4 problems from this positive definiteness. I already discussed about those things. And then from week 7, from VCA, there can be some questions. Those are like a theory-based question from the PCA, and then there can be question where the data point will be given, and then you need to will be asked to calculate like maybe the projection or the projected variance. Those type of problems will be there. And from the 8th week, as already Ram has discussed, maybe you can get some problem from the Taylor series or the like the problem he has discussed in the end, like the largest point you need to, there's ellipse, and then you need to fit the rectangle, and what would the maximum area or such type of problem can be there. So what I was suggesting you, just go through the last term papers, like maybe the last 2-3 terms of paper. Just solve those papers, you'll be getting the idea which type of problems every time it's coming from those portions. Okay, that will help you a lot if you're just going through the last term paper. Just go through the mock, try to solve for the week 7 and week 6. Just solve the graded and practice assignments. Just go through the solution once again for all the 4 weeks. Okay, solve the 4 weeks practice and graded, solve the mock, and then the last term papers. Whatever the time you have, if you're doing this much, I guess none of the problems you'll not be able, like you'll be able to solve all the problem in the exam. Okay.
Thank you, sir.
Yeah, thank you. Yeah, thanks a lot for joining.
Thank you, sir.
Yeah. Okay. Thanks.
Thank you a lot, sir.
Thank you all. Okay.
Thank you, sir.
Thanks, sir.
Good night.
Yeah. Good night, everyone, and go and enjoy IPL.
Good night, sir.
Yeah.
Hello.
Yeah.
Sir, question paper is 50 marks or 100 marks?
It is a 50 or 100, doesn't matter. Like if this is a 50 marks, the weightage will be counted, right? So mostly it will be 50 marks only.
Okay. Just worried about if 100 marks, more questions will be there, sir.
No, there are 15 questions, 1 5.
Okay, sir.